Securing cloud environments involves understanding key security principles and implementing robust control measures. This approach ensures organizations can protect their resources, manage identities effectively, and maintain the integrity and availability of their data. In this course, you will learn about privileged access and the principle of least privilege, which are critical for protecting against security threats. You will also cover the fundamentals of confidentiality, integrity, and availability, essential components of a robust security framework. Next, you will explore various security measures to protect cloud resources. You will compare on premises security with cloud security and examine the different cybersecurity threats that organizations face today. Additionally, you will gain insights into the security infrastructure of Google data centers and how they ensure the safety and reliability of their services. Finally, you will go deep into Google Cloud's product for role based access control, namely the Identity and Access Management Service. You will study the different types of principles in Cloud IAM and the various roles they can assume. By differentiating between basic, predefined, and custom roles, you will learn how to manage identities and access effectively, ensuring that only authorized users have access to sensitive information. We will begin our conversation about trust and security on the Google Cloud by introducing some important security related terms and concepts. Under the shared responsibility model, the cloud provider, like Google, is responsible for the security of the cloud, while the end customer is responsible for security in the cloud. Let's introduce three terms which define responsibilities of the cloud provider in this context. Let's start by talking about hosting, which in the context of cloud responsibilities refers to providing the necessary infra and platform services required to deploy and run applications. The cloud providers, like the Google Cloud, will offer scalable and reliable compute services such as VMs, containers, and serverless functions so that other organizations can host their apps and services on the cloud. The cloud providers will ensure that the infra is highly available, resilient, and capable of handling varying levels of traffic. The next term here is safeguarding. In this context, this encompasses security measures and protocols that the cloud providers implement in order to protect data and apps from threats and unauthorized access. This includes the physical security of data centers, network security, encryption of data at rest and in transit, identity and access management, and compliance with industry standards and regulations. And a third responsibility of the cloud providers is serving. This refers to delivering apps and services to the end users efficiently and reliability. The hyperscalers will ensure that the apps hosted on their platforms are accessible and performant. They will use technologies like content delivery networks, load balancing, and auto scaling. These services will help to distribute the data, reduce latency, and remain responsive even during peak usage times. Cloud providers also need to offer robust APIs and integration tools so that there is seamless interaction between customers and the cloud. These are the responsibilities of the cloud provider, and we can see that all of the responsibilities under the safeguarding heading come down to providing adequate trust and security. Safeguarding is a heavy responsibility because cloud security has become very important, and cloud security itself has multiple dimensions. One of these is data protection. Cloud security is crucial for safeguarding sensitive and personal data from unauthorized access, breaches, and leaks. Robust security measures such as encryption, identity and access management, or IAM, and data masking help cloud providers to ensure that data remains confidential and protected against malicious activities. This is vital for maintaining customer trust, as well as for our second axis, which is regulatory compliance. Many industries are subject to stringent regulations about data privacy and security. These include GDPR, HIPAA, PCI DSS, and many more. Cloud security helps organizations meet these regulatory standards by providing the necessary tools and controls to ensure compliance. Failure to comply with these regulations can result in significant fines, legal penalties, and damage to an organization's reputation. Cloud security also helps to ensure business continuity. It does so by implementing disaster recovery plans, redundancy, and robust backup solutions, which taken together ensure the availability and reliability of cloud services. This is maintained even in the face of cyber attacks, natural disasters, or system failures. Finally, the mitigation of cyber threats is becoming a more and more important consideration. These days, cyber threats such as malware, ransomware, and distributed denial of service attacks are proliferating. Effective cloud strategies to cope with these include advanced threat detection, real time monitoring, and incident response mechanisms to identify and mitigate these threats promptly. In the domain of secure software design, there are several principles of security design. These include principles of least privilege, segregation of duties, defense in depth, resiliency, economy of mechanism, complete mediation, and so on. From this long list, there are three in particular that we need to discuss here. These are the idea of privileged access, least privilege, and zero trust architecture. We'll talk about each one of these in turn. Let's start by talking about privileged access. The principle of privileged access refers to granting elevated permissions to specific users or systems that require access to sensitive data or critical functions. This type of access should not be granted to everyone. It is typically reserved for administrators or service accounts that need to perform tasks beyond those allowed for regular users. Managing privileged access involves strict controls and monitoring in order to prevent misuse or unauthorized activities, thereby ensuring that only authorized entities can perform high level operations. So, at the heart of the principle of privileged access, we have elevated permissions for users or systems that perform critical tasks such as configuring systems, managing user accounts, and accessing sensitive data. These permissions need to be granted only to administrators, specific IT staff, and service accounts that require extensive control over the IT environment. Characteristics of privileged access include the ability to bypass standard security controls, execute system level commands, and make significant changes to system settings. This level of access is essential for maintaining and managing IT infrastructure, but it is accompanied by significant responsibility and risk. Why does this principle make sense? Well, privileged access is necessary in order to ensure that critical admin tasks can be performed efficiently and effectively. For instance, system updates, security patches, and user account management require elevated permissions to implement changes without disruption. This level of access allows administrators to maintain system stability, enhance security, and support enterprise operational needs. Without privileged access, it would be challenging to manage and secure complex IT environments and lead to greater inefficiencies and vulnerability. However, as the line from the movie goes, with great power comes great responsibility. And so, managing privileged access requires a robust strategy to prevent misuse and unauthorized activities. These might include strict access controls, regular audits of access permissions, and the use of tools like privileged access management solutions to monitor and manage privileged accounts. It's also important to enforce strong authentication methods such as multi factor authentication and also to provide regular training to the administrators on security best practices. Authorization is also crucial in order to ensure that only the appropriate individuals have access to critical systems, and auditing is needed to make sure that their actions are logged and monitored for suspicious activity. As an example of privileged access, consider a system admin who has root access to the company's server infrastructure. This admin can install software updates, configure network settings, and manage user permissions across the entire network. Such access is critical for maintaining the security and functionality of the IT environment, but in return, this level of access also needs to be carefully managed in order to ensure that it is not misused either accidentally or intentionally. And this can be done by implementing stringent controls and regular audits. Clearly, there are risks associated with implementing privileged access. These include the potential for abuse, either by malicious insiders or through compromised accounts. If a privileged account is hijacked by a cyber attacker, for instance, they could gain unrestricted access to sensitive data, systems, and network resources, leading to significant security breaches. Additionally, errors or misuse by privileged users can result in accidental data loss, system downtime, or exposure of sensitive information. To mitigate these risks, it is essential to implement strong access controls, continuous monitoring, and incident response plans. We introduced the term privileged access and understood why it's required in any cloud environment. Now we have to talk about the principle of least privilege. Without this counterbalancing principle, privileged access can become very dangerous indeed. The principle of least privilege dictates that users and systems should be granted the minimum level of access necessary in order to perform their functions. By limiting access rights, this principle reduces attack surfaces and minimizes the potential damage from accidental or malicious actions. Implementing this principle of least privilege involves regularly reviewing and adjusting permissions to align with current roles and responsibilities, thereby increasing overall security. We should think of least privilege as a sort of check and balance on the idea of privileged access. Privileged access is required for efficient functioning of a cloud environment. Least privilege is required in order to ensure that the risks of privileged access do not go out of control. Let's understand this in a little more detail. The principle of least privilege ensures that users and systems are only given the minimum level of access required for their duties. So, in order to implement this principle, we should be looking to minimize the number of users or accounts with elevated permissions. This reduces potential entry points for malicious actors. Characteristics of a system that implements this principle include role based access controls, granular permission settings, and continuous review of access levels. By tightly controlling access rights, enterprises can limit the potential damage from both accidental and deliberate security incidents. Least privilege is absolutely essential for enhancing security by balancing the idea of privileged access and reducing the attack surface. By limiting access to only what is necessary, organizations can prevent unauthorized access to sensitive data and critical systems. It also reduces the risk of insider threats because users do not have unnecessary permissions that could be exploited. However, implementing this principle might be more difficult than it sounds. Implementation requires careful planning and ongoing management. Considerations here include defining clear access policies, implementing robust identity and access management systems, and conducting regular audits of access rights. It's also important to provide training and awareness programs to ensure users understand the importance of following access control policies. Continuous monitoring and the constant readjustment of permissions as roles and responsibilities change are what make this implementation most challenging. As an example of this principle of least privilege, consider a customer service representative in a financial institution who only has access to customer account information necessary for their role. They do not have permissions to alter account balances, initiate transactions, or access other sensitive financial data. This restricted access ensures that the representative can perform their job effectively while minimizing the risk of data breaches or financial fraud. If their role changes, the access rights are updated immediately and accordingly in order to match their new responsibilities. Implementing the principle of least privilege correctly is a lot of work. However, not implementing this principle correctly has tremendous risks. Failing to implement this principle can lead to increased exposure to insider threats and greater potential for accidental or intentional misuse of data. Without this principle of least privilege, users may have access to sensitive information or critical systems that they do not need. That makes it easier for attackers to exploit these unnecessary permissions and result in data breaches, financial losses, and significant damage to an enterprise's reputation. Additionally, it might also result in non compliance with regulatory requirements that can lead to legal penalties, the loss of customer trust, fines, and disruptions of business. So, we've now seen that privileged access is necessary for smooth functioning. However, it must be counterbalanced and accompanied by implementing the principle of least privilege. Another relevant control mechanism here is a zero trust architecture. This is a cybersecurity framework that eliminates implicit trust, so it assumes that any potential user, whether human or system based, could be compromised. This approach requires continuous and explicit verification of every user attempting access to an organization's network. Upon gaining access, users are granted the least amount of privilege necessary to perform their tasks. Zero Trust prioritizes user identity over location of the access attempt. The Zero Trust architecture is itself based upon some principles. The first of these is to always assume a breach. The Zero Trust model operates on the principle that any user could be compromised and that a breach is always possible. This assumption leads to a proactive approach to security where the system does not inherently trust any user. By assuming that a breach is inevitable, organizations can implement more robust security measures to detect and mitigate threats and thereby reduce the potential impact of an attack. A second principle of the Zero Trust architecture is to always verify explicitly. So, Zero Trust requires that all users, both human and non human, continuously verify their identities before gaining access to the network. This explicit verification process involves a multi factor authentication and other stringent validation methods to ensure that users are who they claim to be, and that this is checked every time they attempt to access resources. Continuous verification helps to prevent unauthorized access and ensures that only legitimate users can interact with the network. Zero trust architectures also inherently will implement the principle of least privilege. That's because after users are authenticated, they are only granted the minimum level of access necessary in order to perform their specific tasks. This principle of least privilege limits access rights of users and reduces the risk of insider threats. By restricting access to only what's essential, enterprises can better protect sensitive data and critical systems. Collectively, these three principles will implement a zero trust architecture, which in turn helps to reinforce a robust security posture and makes it difficult for attackers to gain access to and exploit resources within the system. These are the principles that underlie a zero trust architecture. Let's now turn to its actual architectural building blocks. The first building block is a system for identities. Remember that all access attempts need to be authenticated as well as authorized. Authentication involves checking the identity of the accessor. Authorization involves checking whether that particular access is allowed. But authentication is only possible if we have a robust system of identities. Here, the digital identity includes all of the data that represents an entity online. Users, devices, applications all need to have identities. In a zero trust framework, organizations must verify the digital identities of all entities before they grant any access. Methods for establishing identities include strong authentication and behavioral analysis to ensure authenticity. Continuous monitoring with real time detection and automatic remediation are essential as well. The zero trust architecture also has strict requirements in terms of devices. Organizations must scrutinize devices before allowing them access to network resources. It's also crucial to have an inventory of all devices operating within the network, and it must be ensured that these are functioning correctly. Implementing this requires a regular checks on device health and compliance help to confirm that those devices are secure and only running approved software. This vigilance again is a lot of work, but it prevents compromised devices from becoming entry points for security breaches. The zero trust architecture requires network segmentation. This involves dividing the network into isolated segments, each controlling access to sensitive data based on user roles and data types. By restricting access to only necessary network segments, enterprises can limit potential damage from breaches and ensure that users only interact with that parts of the network that are essential for their role. Next, in terms of applications and workloads, access of applications to sensitive systems and data must be minimized. Now, of course, applications do need access to sensitive systems and data simply in order to function. But what's important is regular audits to ensure that apps are up to date with the latest security patches and also that vulnerabilities are being constantly scanned for and detection of threats is taking place. Continuous monitoring helps to detect unauthorized access attempts and ensures that apps operate securely and do not become weak points within the network. Finally, access to data is carefully controlled. This involves identifying and classifying data based on its sensitivity. Access to sensitive data needs to be strictly limited to users who need it for their job functions, adhering to the principle of least privilege. In addition, encryption of data both at rest and in transit is very important in order to prevent unauthorized access. All of these pillars taken together will help an enterprise implement a zero trust architecture. Let's now turn our attention to how cloud platforms can help protect against security threats. There are three specific terms here that we need to introduce. The first is security by default, the second is the idea of a security posture, and the third is cyber resilience. Let's define these and talk about each in turn, starting with security by default. Security by default refers to the practice of implementing security measures as a standard configuration rather than as an optional add on. This approach ensures that systems and applications are secure out of the box and embeds robust security features right from the get go. Under the paradigm of security by default, security needs to be built in right from the beginning, that is, right from the initial design phase, rather than being added later. Security measures should aim to address the root cause of security problems and not just its symptoms. This principle will ensure that underlying vulnerabilities are identified and resolved and prevent recurring issues. The security process is a continuous and ongoing one. So, security is not a one time goal, and this ongoing approach will involve regular updates, monitoring, and improvements to adapt to evolving threats. The system will need to strike a balance between usability and security. Security measures should not compromise the usability. However, products need to be secure enough while maximizing ease of use. Default security settings must provide a robust protection without requiring users to make complex adjustments. So, in other words, security should not require extensive reconfiguration in order to be effective. It should work reliably right out of the box. And finally, security threats are a moving target, and in order to keep pace with them, security measures also need to keep evolving. Next, let's turn to the concept of security posture. This defines the overall security status of an organization's networks, information, and systems based on the effectiveness of its security controls and protocols. A strong security posture implies that the organization is well prepared to prevent, detect, and respond to security incidents. A strong security posture has many different elements. The first of these is the existence of detailed security policies. These comprehensive security policies are a must in order to provide a clear framework for how an organization will protect its assets and manage security risks. These need to outline rules, procedures, and responsibilities to ensure that all employees understand their roles in safeguarding information. A second element of a strong security posture is a categorized asset inventory. This needs to include all hardware, software, and data, and this is crucial for effective security management. Third, it's important for clear access controls to exist. These need to include role based access control, strong authentication using, say, multi factor authentication, and regular access reviews. Access controls help prevent unauthorized access and reduce the risk of data breaches. The enterprise must have robust risk management, which includes a process to identify, assess, and mitigate potential security threats. This risk management process must also regularly evaluate vulnerabilities, implement risk mitigation strategies, and continuously monitor for new threats. When security incidents do occur, the response needs to be systematic. Having a systematic incident response plan ensures that organizations can quickly and effectively respond. Of course, the opposite of a systematic incident response is an ad hoc incident response. Avoiding an ad hoc response requires predefined procedures for detecting, reporting, and addressing incidents, as well as plans for how to recover from them. There is a framework known as the GRC framework, where GRC is an acronym for Governance, Risk, and Compliance. Implementing GRC processes helps enterprises take a holistic approach to maintaining a strong security process. The next term that we need to be aware of is cyber resilience. This refers to the ability of the enterprise to withstand and recover from attacks. Resilience is all about recovery from attacks, and cyber resilience is a concept that brings together business continuity, the security of information systems, and organizational resilience. Cyber resilience may be understood using a life cycle where the phases are strategy, design, transition, operation, and evolution. Once again, the key underlying idea here is that the enterprise needs to be resilient. That is, it needs to have the ability to withstand attacks and then recover from them. And this life cycle helps to map out an organization's response to such threats. Let's now go from the general to the specific and outline three specific security measures that are used to commonly protect cloud resources. These are firewalls, encryption, and decryption. Let's talk about each one of these in turn. A firewall effectively is a barrier between our internal network and external resources such as the internet. It serves to prevent unauthorized access and attacks and monitors and filters both incoming and outgoing network traffic. This monitoring and filtering happen on the basis of predefined security rules and taken together ensure that only legitimate traffic is allowed through. By controlling the traffic flow, firewalls help protect cloud resources from malicious activities and unauthorized access attempts. Firewalls today rely on something known as stateful packet inspection. This is widely used in modern firewalls to inspect the state of active connections and make decisions based on the context of the traffic. Unlike simple packet filtering, which examines each packet in isolation, stateful inspection evaluates the state and attributes of the entire session. This provides a more sophisticated and dynamic method of filtering traffic and increases the firewall's ability to detect and block complex threats. Firewalls also rely heavily on rule based access control. They use a set of rules that have been configured by admins in order to control the flow of network traffic. These rules will specify criteria such as IP addresses, port numbers, and protocols that are permitted or denied access. By enforcing these rules, firewalls can effectively block malicious traffic and only allow authorized communication. It is through the use of mechanisms like rule based access control and stateful packet inspection that firewalls achieve their end goal, which is traffic monitoring and filtering. The end goal of firewalls is to monitor both incoming and outgoing network traffic and prevent unauthorized access and attacks. Another term and technology that is heavily used in cloud security is encryption. This is the process of converting data into a coded format in order to prevent unauthorized access. On the cloud, encryption ensures that the data remains confidential and secure both at rest and in transit. At rest implies when the data is stored, and in transit implies when the data is being transmitted over networks. Only authorized users with the correct decryption keys can access the original data, protecting sensitive information from being read or tampered with by unauthorized parties. In terms of mechanics, encryption is actually the process of converting plain text data into a coded format that's called ciphertext. This is done using an algorithm, that's the encryption algorithm, and a key, that's the encryption key. This transformation ensures that the data is unreadable to anyone who does not have the correct decryption key. Encryption is a fundamental security measure and it's used to protect sensitive information from unauthorized access in a wide variety of systems and use cases. The algorithm that's used to perform the encryption is known as a cryptographic algorithm, and common examples include AES, that's the Advanced Encryption Standard, or RSA, that's Rivest, Shamir, and Adelman. These algorithms use an encryption key to transform plain text into ciphertext. The encryption process can occur at various stages, such as when the data is at rest, that is stored data, or when the data is in transit, that is when the data is being transmitted over the network. Many cloud products will encrypt both in transit and at rest, and this ensures optimum protection. The way encryption algorithms work, it's not possible to go from the ciphertext back to the original content. So even if the encrypted data is intercepted by a malicious actor, it remains unreadable and useless without the decryption key. And this is how encryption helps to safeguard sensitive information from unauthorized access. It ensures both confidentiality and integrity, and provides a secure way to store and transmit sensitive information across networks and systems. Encryption, of course, is closely related to decryption, which is the process of converting the encrypted data back to its original format so that it can be read and used by authorized users. In the context of cloud security, decryption ensures that encrypted data is accessible only to those with the appropriate decryption keys. This process is essential for maintaining data confidentiality and integrity, and it too ensures that sensitive information is protected while still being available for legitimate use. Decryption is the process of converting the encrypted data, that is the ciphertext, back into its original readable format, that is plain text, using the decryption key. This process effectively reverses the encryption and it allows authorized users to access and understand the secured information. Decryption is essential for accessing protected data and can be used as intended by legitimate users. Decryption is also performed using a cryptographic algorithm. In fact, the same cryptographic algorithm that's used in encryption but in reverse, along with the appropriate decryption key. For instance, if the data is encrypted using the AES algorithm, then it must be decrypted using the same algorithm and the matching key. The decryption key is typically only known to authorized users or systems, ensuring that only they can revert the ciphertext back to its original plaintext form. Where encryption ensures that unauthorized users are not able to read the data, decryption ensures that authorized users are able to read the data. And in this way, decryption helps with the availability of data. It also helps to maintain data confidentiality and integrity. This process of encryption and decryption taken together is vital for secure communication, data storage, and compliance with privacy regulations. Next, we are going to talk about the CIA triad and its role in information security. CIA here is an acronym for confidentiality, integrity, and availability. This is a fundamental model in information security because these three attributes effectively stand for independent dimensions along which we can measure the security of our data. Confidentiality ensures that sensitive information is accessible only to authorized individuals, protecting it from unauthorized access and breaches. Integrity involves maintaining the accuracy and completeness of the data, ensuring that it is not altered or tampered with by unauthorized parties. Availability ensures that information and resources are accessible to authorized users when needed. This involves preventing disruptions to operations and ensuring continuous access to critical data and systems. Taken together, these three principles or attributes form the cornerstone of a robust security framework. Let's take each of these in turn, starting with confidentiality. This ensures that data remains private and secure, and access is only given to authorized individuals or roles. Without confidentiality, sensitive information would be exposed to anyone. This would lead to potential data breaches and significant security risks. Confidentiality is maintained using various mechanisms such as permissions, authentication, authorization controls, and protection of both internal and external data from unauthorized access. Let's talk about some control measures that can be taken to ensure confidentiality. The first of these is data access control. Confidentiality requires that access to data be restricted only to authorized individuals or roles, and that in turn requires implementing strong access control mechanisms such as role based access control as well as multi factor authentication. A quick word here on the difference between authorization and authentication. Authentication involves verifying the identity of a user. Authorization, on the other hand, involves checking that whatever operation the user is trying to perform is actually allowed. Multi-factor authentication helps with authentication. Role-based access control helps primarily with authorization. Both are important in creating secure data access controls. Another commonly used technique is encryption, which we briefly discussed. This is a critical component of maintaining data confidentiality. By converting plain text data into ciphertext using cryptographic algorithms, encryption ensures that even if data is intercepted during transmission or storage, it remains unreadable without the decryption key. This protects sensitive information from being accessed or disclosed by unauthorized parties and directly safeguards data privacy and security. There are various other mechanisms used to maintain confidentiality, and two of these are data masking and anonymization. Masking involves altering the data to hide its original content, while anonymization removes personally identifiable information or other sensitive information in order to protect privacy. These techniques are particularly important when sharing data for testing, analysis, or compliance purposes, and also when making use of production data in test systems. Next, let's turn to integrity. This attribute focuses on the accuracy, consistency, and trustworthiness of data. In order for data to maintain its integrity, it is important that it not be tampered with by unauthorized users. There are several mechanisms that can be used to enforce integrity, including hashing, digital signing, code signing, and authenticity checks. Confidentiality is primarily focused on not allowing unauthorized users to access the data. Integrity is primarily focused with not allowing unauthorized users to modify the data. So, ensuring integrity involves keeping the data accurate and trustworthy. This requires the information to be unchanged and reliable throughout its life cycle. Data should not be altered or corrupted, regardless of where it is stored or how it is moved around. The key to ensuring integrity is the prevention of unauthorized modifications. Here, for instance, systems need to be in place to ensure that messages are not altered during delivery. As discussed, techniques such as hashing, encryption, digital signing, code signing, secure communication protocols, and stringent access controls are all relevant in this context. A wide variety of data integrity controls exist. We've already mentioned some of these, such as checksums, hashes, and digital signatures. And the common theme underlying all of these is that some unique values are generated based on the content in the data. That unique value is then transmitted separately, and it can be verified by the recipient in order to ensure that the unique value matches the content. Any mismatch between the hash or the checksum and the original message is a sign to the recipient that the data is no longer trustworthy and that its integrity has been compromised. Let's move to the third pillar of the CIA triad, which is availability. This involves ensuring that systems, apps, and data are available and accessible when needed. This is how continuous business operations and customer access are protected. The enemies of availability are downtime or system inaccessibility. These may or may not be caused by security related incidents, but however they are caused, they lead to disruption in business processes. Maintaining availability focuses on robust infra, redundancy, disaster recovery plans, and the like. Cloud services are excellent at maintaining availability largely through the use of replication and redundancy. Let's talk about these mechanisms. Redundancy involves duplicating critical components and systems within an IT infrastructure to ensure continuous operation even in the case of failure. By having backup servers, network connections, and power supplies, organizations can mitigate the risk of single points of failure. Redundant systems ensure that even if one component fails, another can seamlessly take over, maintaining service availability. Redundancy is closely related to the need for robust failover mechanisms. These are the systems which will automatically switch to the standby system or component when the primary system fails. It's important that this transition be seamless in order to ensure that services remain uninterrupted and available even in case of hardware or software malfunctions. Failover mechanisms include clustering and load balancing, and these improve the reliability and resilience of IT systems. Another aspect of ensuring availability is having disaster recovery plans which outline processes and procedures that an organization must follow to restore operations in the aftermath of a catastrophic event, such as natural disasters, cyber attacks, or large scale system failures. These plans typically include data backups, alternate communication channels, and predefined recovery steps to minimize data loss and downtime. Finally, it's worth emphasizing here that the whole point of ensuring availability is to minimize downtime. When we frame availability in terms of downtime, we also realize that there are other measures that can be taken to improve availability. These include proactive maintenance, regular updates, and the use of monitoring tools to identify and address potential issues before they lead to outages. The CIA triad is truly foundational in information security. In fact, some definitions are based on the CIA triad. Let's quickly talk about the strengths and weaknesses. Some of the strengths of this triad include simplicity. The CIA triad provides a straightforward and easy to understand framework for ensuring information security. Unlike more complex models and frameworks that can be quite overwhelming, the triad focuses on three clear principles: confidentiality, integrity, and availability. What's important also is that these three represent independent dimensions of data security. That in turn leads to a balanced approach by giving equal importance to each of the attributes. Unlike some frameworks which prioritize security and protection above all else, often at the expense of operational efficiency, this framework ensures that security measures do not hinder business operations. That comes in through the importance of availability, which focuses on the availability of data and systems for legitimate use. Like many good frameworks, the CIA framework also is flexible and open ended and adaptable. It's not rigid, it does not have a fixed end goal. Instead, it can adapt to the evolving needs and threats facing an organization. Let's now quickly turn to a conversation of some of the weaknesses that have been identified with this particular framework. The first is the limited scope. Because the CIA triad focuses primarily on these three attributes, it does not encompass other aspects of security threats. For instance, it does not directly address social engineering or phishing attacks that target employees, which could be significant security threats. Enterprises, therefore, should also implement additional training programs and other measures focused on human centric threats. A second cited weakness is the lack of specificity. The three attributes or principles are fairly high level, and so organizations might struggle to build a comprehensive security model based solely on the CIA triad. In this particular case, more detailed frameworks and a list of best practices can be used in order to create effective security measures. Finally, the CIA triad is not holistic. Academic studies have pointed out, for instance, that it does not include some other important attributes such as privacy. Privacy and non repudiation neither is completely expressible in terms of the CIA attributes. Therefore, enterprises should look to establish robust security processes and use the CIA triad in conjunction with other models and frameworks such as risk management frameworks, security controls, and compliance standards and regulations. It's important here for us to introduce and contrast two terms, control and compliance. Control refers to measures and processes taken by an enterprise to manage and mitigate security risks. Compliance, on the other hand, refers to the process of adhering to industry regulations, legal requirements, and organizational policies. Controls help you to do the right thing, compliance help you prove that you are doing the right thing. In the context of cloud security, control measures include robust authentication mechanisms, access restrictions, and security awareness training for employees. When it comes to compliance, the cloud providers can be a crucial source of support. They will offer compliance frameworks and certifications in order to help enterprises prove that they are meeting their regulatory obligations. In the era of the transformation cloud, there are subtle differences between security on prem and security on a cloud. Let's go ahead and examine some of these, starting with characteristics of on prem security. In an on prem environment, an organization has complete control and trust over their hardware, software, and network components. This fosters an overall very high level of trust and confidence within their premises. Enterprises can customize their security measures to fit specific needs and regulations. There's no need or very little need to rely on external providers. This control ensures that data privacy, integrity, and confidentiality are strictly maintained. However, the flip side of this control is the responsibility. The responsibility for security management and updates falls entirely on the organization and requires dedicated IT staff and resources. On premise security also involves offline security measures and infrastructure components that are hosted on site, making it harder for attackers to breach network parameters. Physical security measures such as security personnel and restricted access to premises add additional layers of protection. This physical barrier is a significant advantage over online only security measures. However, this again has a flip side. It means that any physical damage or disaster affecting the premises can severely impact the security and availability of the data. We see a theme here. There is more control in an on premise setting, but that comes at a certain cost, and one of those costs is higher operational costs. These are significantly higher compared to cloud based solutions. Enterprises must invest in purchasing, maintaining, and upgrading their infrastructure equipment, as well as in hiring skilled personnel to manage security. These costs can become quite a burden, especially for small and medium scaled businesses. For many organizations, however, this investment is justified by the higher level of data privacy and control over their security environment. A characteristic of on prem environments is a dependence on internal resources. The management and maintenance of on premise security solutions depends entirely on the organization's internal resources. This could be advantageous because it allows for tailored security protocols and quick adjustments, for instance, in order to meet specific regulatory requirements. Once again, this is a double edged sword. It means that the organization must continually invest in training and retaining skilled IT staff in order to handle security tasks. This reliance on internal resources can also strain the organization's capacity to respond as the external environment changes. The characteristics of cloud security are quite different. The first and primary characteristic is the scalability and flexibility of the cloud. Cloud security leverages global data centers to manage security and content at scale. This provides organizations with scalability and flexibility in their security solutions. Businesses can easily adjust their security resources based on current needs, whether scaling up during peak times or down during off peak times. In particular, this scalability represents a significant advantage over on premise physical security and controls, which require physical hardware to be maintained and controlled. However, this also gives rise to a reliance on an internet connection. This could be a drawback, especially in areas with unstable connectivity or in situations involving disasters. Cost effectiveness and efficiency are likely attractions of the cloud. Cloud security can be expected to be more cost effective than on premise infrastructure because organizations will save on upfront costs of hardware and the ongoing expenses of maintenance, upgrades, and dedicated IT staff. In addition, the hyperscalers typically offer subscription based models for many important services so that businesses will only pay for the resources that they actually use. Nonetheless, there might still be hidden costs and the potential for misconfiguration of cloud services, which in turn can lead to fluctuating fees. The cloud platforms have been evolving their security features for a long time, and that now allows them to offer very enhanced and advanced security features such as identity and access management, data governance, legal compliance support, risk mitigation, data recovery, and backup. The continuous updation and patching of security protocols by cloud providers offers an additional layer of protection. However, we should keep in mind the shared responsibility model. The cloud provider is responsible for security of the cloud. Organizations are still responsible for security in the cloud in terms of correctly managing access and having the right security protocols in place. The leading cloud partners are global in their accessibility and scale, and as a result, businesses which leverage the cloud can connect digitally with customers, partners, and employees everywhere. This is an opportunity because it improves operational efficiency and supports remote work environments. However, it can also introduce new risks such as increased exposure to cyber threats and data breaches. Let's try and sum up all of these points of similarity and difference. In the on prem model, security is managed on site. In the cloud security model, it's managed off site. In the on prem world, the organization is responsible for securing both infra and data. In the cloud world, there is a shared responsibility model where the cloud provider is responsible for security and the organization is responsible for data. In the on prem world, scaling up operations requires significant new investments in infra and additional hardware. In the cloud world, businesses can quickly adjust resources up and down. In operational terms, a big difference is that in the on prem world, the enterprise is responsible for maintenance and updates. In the cloud world, that responsibility typically shifts over to the cloud provider. A lot of the other differences between on prem and cloud security are similar to general differences between on prem and cloud. On prem security requires significant upfront capex. Cloud security operates on a pay as you go model. Similarly, in the cloud model, Software is stored, run, and managed on infra provided by the cloud provider. And likewise, in the cloud world, enterprises have less than complete control of their data. Security solutions can be customized much more extensively on prem than in the cloud world, where we are limited by the services offered by the cloud provider. And finally, flexibility and scalability are somewhat limited in an on prem setting, but are much more easy to obtain in the world of cloud security. Next, let's talk about cybersecurity threats. These are malicious activities or events that aim to compromise the CIA properties of an information system. There is a long list of different types of cybersecurity threats. Here are some of those types on screen. Let's talk about them in turn, starting with social engineering attacks. These involve manipulating individuals into divulging confidential information or performing actions that compromise security. Social engineering attacks themselves have many subcategories, which include phishing emails, pretexting, or baiting. Let's talk about some of these subcategories. The first is phishing. This involves sending deceptive emails or messages that appear to come from legitimate sources in order to trick recipients into providing sensitive information like login credentials or financial details. The attackers will often use urgent language and fake websites that closely mimic real ones. Spear phishing is a more targeted form of phishing where the attackers customize their messages to a specific individual or organization. By gathering information about the target from social media and other sources, they create very convincing and personalized messages. This personalization makes such attacks very difficult to detect and resist and often leads to a higher success rate. Pretexting involves creating a fabricated scenario or pretext in order to manipulate a victim into divulging information or performing compromising actions. The attackers will often pose as authority figures such as company executives, IT staff, or law enforcement officers. Another form of social engineering is baiting. This uses the promise of a reward or even just the lure of curiosity to trick victims into performing compromising actions. This might involve leaving infected USB drives labeled with enticing descriptions in public places or offering free downloads of desirable software or media online. Once the victim takes the bait, malware will be installed on their device, giving the attackers access and an entry point. Next on our list of cybersecurity threats is physical damage. This refers to intentional destruction or sabotage of hardware or infrastructure. It could include acts like breaking into a facility to destroy servers, cutting cables, or tampering with physical devices. Let's quickly talk about some forms of physical damage. Hardware damage might result in direct damage to hardware such as servers, storage devices, or networking. This damage might be intentional, as in sabotage or vandalism, or even unintentional, resulting from accidents. Protecting hardware from such threats requires robust physical security controls, including surveillance, access controls, and secure housing for critical infra. Power disruptions, which might be either due to outages, surges, or deliberate attacks on power supplies, can severely impact an organization's operations. To mitigate this, enterprises must invest in backup power solutions such as UPS and generators, as well as redundant systems. Natural disasters include floods, fire, and earthquakes, and in order to safeguard against these, organizations must have comprehensive disaster recovery plans, off-site backups, robust data replication, and resilient infra designs. Malware, viruses, and ransomware. These are familiar terms. Malware tends to steal sensitive information, viruses often corrupt data, and ransomware can often lock users out of systems until a ransom is paid. A quick word on each of these. Malware, which is short for malicious software, is a pretty broad category. Examples include spyware as well as adware, which generates unwanted ads. Malware can spread through infected emails, malicious websites, or compromised software downloads. Viruses are a specific type of malware that often attach themselves to legitimate files or programs and spread by infecting other files on the same or connected systems. Once activated, a virus may corrupt, delete, or modify data, disrupt systems, or even render systems unusable. Viruses often rely on human interaction, such as opening an infected email attachment or downloading a compromised file. Ransomware is a form of malware that involves encrypting a victim's data and then demanding payment. This payment is usually demanded in cryptocurrency in exchange for the decryption key. Victims face a difficult choice of paying the ransom, where there is no guarantee of data recovery, or attempting to restore the systems through backups and other recovery methods. A fourth and important category of cybersecurity threats is vulnerable third party systems. Many organizations rely on vendors for various services, and vulnerabilities in the systems available through those vendors may be exploited by attackers. Vulnerable third party systems can serve as a gateway for attackers to gain indirect access to data. They can also lead to supply chain attacks, where attacks on the vendor lead to malware being spread to all of the customers of the vendor. And a serious risk here is that of our enterprise becoming non compliant with laws and regulations because of issues with third party system. Configuration mishaps are another very important source of vulnerability. Improperly configured systems, networks in particular, and applications in general can lead to security gaps that attackers are always looking to exploit. Common configuration mistakes include using default passwords, leaving ports open, or failing to implement proper role based access control. Users often forget that under the model of shared responsibility, the responsibility for correct configuration is on the user. Misconfigured access controls can lead to unauthorized access, for instance, failing to enforce the principle of least privilege by giving users more than the minimum level of access. Weak default settings are another common problem. Default passwords and default security configurations fall into this category. Finally, there is improper privileged access management. Systems which grant privileged access must be accompanied by other systems which will constantly monitor and prevent misuse. Finally, it's worth calling out zero-day exploits, which effectively take advantage of vulnerabilities that are still unknown to the software vendor and have not yet been patched. Attackers use these exploits to gain unauthorized access before the vulnerability is discovered and fixed, and for that reason, they are extremely dangerous and challenging to defend against. Zero-day exploits usually have some combination of undetected vulnerabilities and high-profile targets. The high profile nature of the targets is because zero-day exploits have a very high monetary value, and these tend to be sold on the dark web at very high prices. And that's why attackers tend to save these up for the most high profile targets, which afford them the best opportunity of profit. Now that we have a good general sense of how security on the cloud works, let's start talking about Google's cloud offerings. Let's begin with a conversation about Google's data centers. A data center is a specialized facility that houses a large number of computer servers, storage systems, and networking equipment. Google and all of the hyperscalers build their own data centers, and Google has a wide network of data centers across the globe. These are built using zero trust architecture and have purpose built hardware and software. This means that every access request is thoroughly authenticated, authorized, and continuously validated before any access is granted to data or resources. In addition, Google data centers use segmented networks, they enforce strict access controls, and continuously monitor for suspicious activity. The purpose built servers have tamper evident hardware, secure boot, and hardware based encryption, all of which provide robust security at the hardware level. Google also pays close attention to physical data center security. It makes use of biometric authentication and robust access control. Only authorized personnel can enter secure areas. The principle of least privilege is used to ensure that only individuals with the explicit authorization have access to specific areas within the data center. The data centers are carefully designed to be efficient while still being compliant with the best security norms. These include the purpose-built servers for optimal performance as well as for hardware and software security. We mentioned the tamper-evident hardware, which immediately reveals any unauthorized access or modifications and makes any attempts to interfere with the server immediately noticeable. Secure boot ensures that the server only runs trusted software by verifying the integrity of the OS and the firmware during the boot process. This prevents the execution of malicious code. Hardware-based encryption offers a higher level of data protection, by encrypting data directly on the server using dedicated hardware modules. Google uses a metric known as PUE, that is Power Usage Effectiveness. This is a measure of efficiency in energy and electricity usage. Google is always striving to lower its PUE scores. It also is at the forefront of innovation, for instance, with innovative cooling systems. Google has a data center in Hamina, Finland, which utilizes seawater from the Bay of Finland. Google is also proud, justifiably so, of the scalability and flexibility of its data centers. They can seamlessly accommodate new hardware and software, and they also have massive customization capabilities. We will now talk about secure storage and specifically how the Google Cloud makes sure that data is stored and transitioned securely in its facilities. Encryption is a topic we've already discussed. This involves encoding data into a format that can only be accessed or deciphered by individuals with the correct decryption key. When it comes to encrypting data, it is possible for data to be encrypted when at rest, data to be encrypted when in transit, and finally, it's also possible to encrypt data in use. Let's quickly talk about each of these three terms. Data at rest refers to inactive data that is stored in physical or digital media, such as hard drives, databases, or cloud storage. The GCP uses encryption at rest by default, so all customer content is encrypted at rest. This is free and built in, and it adds additional security to the GCP usage. Encrypting data at rest helps to secure data in different ways. For one, it ensures that if the data falls into the hands of an attacker, it remains unreadable without the appropriate decryption key. This reduces the attack surface of the system, and it also fits into a centralized key management approach. This is possible on the Google Cloud using services like Google KMS. Encrypting data at rest is also a critical privacy mechanism because it makes sure that even systems and engineers have only restricted access. Google encrypts all customer content at rest without any action being required from the user. By default, it makes use of AES 256, which is a robust encryption algorithm. Google manages the encryption keys by default, but it also allows customer managed encryption keys. This is a schematic diagram that shows the several layers of encryption that are generally used in the GCP world. Infrastructure components rely on distributed file system encryption. Databases rely on database and file storage encryption. And also, there is storage device encryption for all data in production data centers. Data is chunked and encrypted, so immediately after the data is uploaded to Google, data will chunk each chunk and then go ahead and encrypt each of those chunks. Those chunks will then be distributed across Google's storage infrastructure. Next, let's move on and talk about encryption of data in transit. Data in transit refers to data that's moving from one location to another, such as over a network or between devices. Encrypting data in transit involves using encryption protocols such as SSL TLS in order to prevent it from interception or eavesdropping during transmission. The GCP encrypts and authenticates data at multiple network layers and uses secure protocols like the TLS to encrypt data at transfer. Google has several security measures for data in transit. It encrypts and authenticates data in transit at one or more network layers each time data moves outside physical boundaries controlled by Google. All VM to VM traffic within a VPC network is encrypted, and so is all peered VPC network traffic. Google also secures communications using TLS. This is the Transport Layer Security, a cryptographic protocol that's designed to provide secure communication over networks. It's widely used in securing browsers, email, instant messaging, and in order to prevent eavesdropping, tampering, and message forgery. For customers who have additional requirements, Google also has more advanced features such as encryption of data over wide area networks. So, in summary, Google will encrypt the data while in transit using TLS. It will ensure that the data reaches its destination unaltered, and at the destination, it will verify the data source. The third type of data encryption is encryption of data in use. As the name would suggest, this is data that's being actively processed by apps, systems, or users. Traditionally, this has been very difficult to do. However, Google has developed a technique known as memory encryption, which locks data inside computer memory, making it nearly impossible for unauthorized users to gain access to it even while it's in use. And this is the basis of a set of features known as confidential computing, which offers the encryption of data in use with performance which is still roughly similar to standard virtual machines. Using memory encryption, confidential computing is available on the GCP in different forms. There are confidential VMs, then confidential VMs with H100 GPUs for AI ML use cases. It's also possible to have confidential GKE nodes if you're using the Kubernetes engine. There's a product known as confidential space, which can be used to aggregate and analyze sensitive data. And then there are also confidential versions of Dataflow and Dataproc, which are great for ETL processes. It's worth reiterating that all data is encrypted at rest on the GCP, and it's AES, or the Advanced Encryption Standard, that's used in this process. AES is a symmetric encryption algorithm. It supports different key lengths, and it's widely used in security-based applications. Next, let's move on and quickly survey some of the Google Cloud products for key management. Once again, let's quickly talk about what cryptographic keys are. A cryptographic key is used to hash the data, and this resulting cryptographic hash digest has some favorable properties. For instance, it is impossible to go from the digest back to the original data, and it's also impossible for different data items to give rise to the same digest. Cryptographic keys play a crucial role in encryption as well as in decryption. They ensure that data is only accessible by the intended recipient because only the intended recipient will have the correct decryption key. For users who'd like a secure mechanism to store their own keys, there is a Google product called the KMS. This is the Cloud Key Management Service. This is a managed service that allows users to create, manage, and use cryptographic keys. These can be used to encrypt data that's stored on the Google Cloud. The KMS supports a range of encryption algorithms and also has automatic key rotation features as well as very detailed audit logs for tracking key usage. Just to be clear, the KMS is separate from default encryption on the Google Cloud. Again, all Google Cloud services store and encrypt data by default without the use of the KMS. So you don't need to perform any configuration, and all of these actions such as key rotation are automatically performed by Google default encryption. If, however, you would like to go with customer managed encryption, then KMS is the product for you. This is a scheme known as customer managed encryption keys. These are keys that customers create, own, and manage within the cloud services for their own purposes. So unlike with default encryption, CMEK gives greater control, but therefore also greater responsibility over the keys. So now the customer will be responsible for key rotation and access policies. And once you switch to a CMEK model, your sensitive data is going to be encrypted using your own customer managed keys, and not even the cloud provider can access the plain text data without authorization. If you do decide for whatever reason that you do not want to go with Google's default encryption and would like to have customer managed encryption, then the Cloud KMS product makes a lot of sense. It integrates tightly with a variety of Google Cloud services and at the same time gives you control over the key rotation schedule, IAM roles, and permissions. Now, if for some reason you decide that the keys generated in the Cloud KMS are not secure enough for you, then you have other services available, notably the Cloud Hardware Security Module. Cloud HSM is an alternative to Cloud KMS. This allows you to create and manage keys, but these keys are hardware based rather than software based. This in turn means that Cloud HSM keys are entirely generated within something known as a hardware security module. This is a tamper resistant bit of hardware with secure enclaves. When might you use Cloud HSM? Well, if your security requirements truly are of the very highest level. Or maybe you have compliance needs, maybe your industry regulation mandates the use of hardware based keys. For most use cases, default encryption is fine. For more advanced use cases, you might want to go with customer managed encryption keys using KMS. And for the highest level of security, you might want to go with the HSM keys. Now, both of those two types of keys are generated by Google. What if you would like to come with your own keys, which are never sent to Google at all? Then you can go with Cloud Enterprise Key Management, or EKM. This is a service that allows you to create external keys and you have control over those keys. They are never shared with Google. So you might want to make use of features like CMEK with keys generated in Cloud KMS for client-side encryption. There is also a feature known as CSEK, that's Customer Supplied Encryption Keys. This is a feature in cloud storage as well as Compute Engine. Here, if you supply your own keys, Google will use those keys to protect the Google-generated keys that are used to encrypt and decrypt your data. And finally, it's worth mentioning that confidential computing, which we briefly mentioned, is supported by Compute Engine, Dataproc, and GKE. Confidential computing products make use of encryption in use, and this requires a separate set of keys. Those keys will not be accessed by Google. Let's now turn our attention from encryption to identity management. In software systems and the cloud, identity is a very important concept. It's extremely important for the platform to know at any point in time the identity of any user, device, or application. Whenever an entity makes any request to access data or to perform an operation, the platform needs to be able to determine who is making this request, then verify that this is an acceptable request, and also log that the request was made. This leads us to the three crucial aspects of cloud identity management: authentication, authorization, and auditing. Let's understand each of these, starting with authentication. This is the process of verifying the identity of a user, device, or app before granting access to a cloud service or resource. This typically involves the use of credentials such as passwords, biometric data, or multi factor authentication. In general, not every system needs to have its own identities. Authentication might also make use of something known as federated identities, where, for instance, you sign in to access a website using your Google account. Whichever way this is implemented, authentication is crucially important because without verifying the identity of users or systems that are seeking access, it is not secure at all to allow that access. Put differently, authentication is the gatekeeper. It's the step that must occur before authorization. There are many different methods of authorization. These include traditional passwords. These are widely used but also vulnerable to attacks. There are more secure methods which include biometric authentication, where users might provide fingerprints or facial recognition, physical tokens such as smart cards or USB security keys. In order to strengthen the authentication process, it's also common to have two-step verification, which is also known as two-factor authentication, or more generally as multi-factor authentication. This makes use of a combination of user signals, such as what the user knows, who the user is, and what the user has. With two-step verification enabled, for instance, the user might have to provide both a password and an SMS one-time password which is sent to their phone. Moving on from authentication, the next crucial aspect is authorization. This is the process of determining whether the permissions and access levels granted to authenticated users allow a particular bit of access. Once an entity has been authenticated, the system will check its assigned roles and permissions to decide what actions that entity can perform and what resources that entity can access. This ensures that only users with the appropriate levels of privilege can perform specific operations. Without authorization, the system would be vulnerable to unauthorized changes, and that would compromise the integrity of the system. On the cloud platforms, authorization is usually performed using role-based access control, although there are also examples of something known as attribute-based access control. To see the role of authorization with an example, consider, for instance, a user who is an employee in the finance department. Such a user has access to financial records but not to HR data, and this ensures that sensitive information is only accessible to those who need it. You can see here that authorization has helped to enforce the principle of least privilege. Cloud systems use role-based access control. Here, authorization is set up to assign different permissions to individuals or groups based on their roles, responsibilities, and organizational hierarchy. This allows the creation of very fine-grained access control to ensure that users can perform very specific tasks and also prevent users from performing other unauthorized actions. For instance, a system admin might have the authority to create and remove user accounts, manage system settings, and access all data, while a standard user might only be able to view and edit their own data. Ultimately, the enforcement of authorization happens using access control rules. These access control rules might be directly specified at the resource level, linking a specific user to a specific resource, or more broadly using role-based access control. A final and equally important aspect of cloud identity management is auditing. We hear the terms authentication and authorization mentioned together all the time. It's not that common to hear auditing mentioned in the same breath. However, it should be. Auditing in cloud identity management involves the continuous monitoring and recording of user activities and access events. This is a crucial step in ensuring compliance with security policies and regulations. It's also very important in order to maintain the principle of least control. Because roles change over time, it is only by auditing that we are able to modulate permissions and access control to different users. Auditing helps to provide detailed logs of who accessed what resources when and what actions were subsequently performed. Cloud providers typically offer built in auditing tools which integrate with their IAM services. So, once again, auditing plays a crucial role. It helps to maintain the CIA triad. It helps to make sure, for instance, that elevated privilege given to certain users is not misused. This could be done by collecting detailed logs of user actions, system events, and other relevant data. Continuous monitoring and continuous surveillance are also required in order for zero trust architectures to be successfully implemented. Auditing helps with the detection and analysis of activity logs. Organizations can search for anomalies, security breaches, and policy violations. They might reveal unusual patterns or unauthorized actions that are indicative of a security threat. Auditing is also extremely important for compliance as well as for the investigation of incidents. Audit records can be used to demonstrate adherence to regulatory requirements, to support forensic analysis after security incidents, and also in order to evaluate the effectiveness of security measures and system performance. Now that we understand identity and access management in general, let's turn our attention to the Cloud Identity and Access Management Service. This is a service on the Google Cloud that allows users to manage identity and access control by defining who, that's the identity, has what access, that's the role, for which resource. So when an enterprise uses the cloud, it needs to create and assign roles to users, groups, or service accounts. This will determine their permissions to access different cloud resources. By defining these roles and permissions, Cloud IAM ensures that only authorized users can perform specific actions on the cloud resources. It's important to point out that Cloud IAM is based on role-based access control. This means that permission to access a resource is not granted directly to the end user. Rather, permissions are grouped into roles, and roles are granted to authenticated principals. In the past, the IAM service often referred to principals as members, and some of the IAM APIs still make use of this term. The important building blocks of the Cloud IAM service are principals, roles, and policies. Let's go ahead and understand each one of these in turn. Within the world of Cloud IAM, the term principal refers to any Google Cloud identity. This could be a user, a group, or a service account. To be even more precise, a principal could be a Google account that represents an end user, a service account, that's the identity of some application or compute workload, a Google group, a Google Workspace account, or a cloud identity domain that can access a resource. All of these are valid types of principals. Every principal has its own identifier, which is typically an email address. The next important building block is that of a role. A role is effectively a collection of permissions. Roles can be predefined by the Google Cloud, such as viewer, editor, or owner. It's also possible to custom define roles to meet specific organizational needs. Every role is basically a logical grouping of permissions, and each permission in turn grants the ability to perform a very specific operation, for instance, reading data, writing data, managing resources, and so on. The third important building block is the policy. This is what binds members or principals to a role. A policy in IAM is a configuration which effectively binds members to a role, which is a group of permissions. So the policy allows every member to perform all of the operations which are allowed by those permissions. This binding mechanism, which links members and roles, ensures that access control is explicitly defined, maintained, and enforced. Because rules usually explicitly allow operations, policies are often also known as allow policies. Here on screen now is an example of how a policy might work in the IAM world. On screen now, we see two examples of how policies might work in the IAM world. On top, we have a role binding, which combines a role and two principals. Those two principals are a Google account, user@example.com, and a service account. The role is the App Engine admin role. The second role binding also binds a role and two principals. The difference here is that one of those principals is a cloud identity domain or a workspace account, and the other is a Google group. And in the second example, the role is a logs viewer role. So in the world of the cloud IAM service, there are principals and there is access. There are different types of principals. These could include Google accounts, service accounts, groups, workspace domains, or cloud identity domains. Let's talk about each one of these in turn. A Google account is an identity that allows an individual to access different Google services. An example of a Google account might be a developer who is using their Google account to log in to the Google Cloud Console. Next comes service accounts. A service account is a special type of account that belongs to an app or a VM rather than representing an individual user. The service account is used to authenticate and authorize apps and services to interact with GCP services. For example, a web app running on Google Cloud might use a service account to access a cloud storage bucket to read and write data. When that particular app runs, it's accessing the cloud storage bucket with the identity of the service account, not with the identity of the Google account of the developer. The service account has its own set of credentials, typically in the form of a key file. The application has to use those credentials in order to authenticate its requests. This allows apps to perform automated tasks and to access resources without requiring individual user credentials. The idea of the service account might seem a little counterintuitive at first, but there are actually many benefits. For one, there is the automated authentication and authorization, which we already discussed. When a particular app is running, it's the identity of the service account and not the identity of the developer that should be used in authentication. This allows the application to authenticate and authorize without human intervention or the entry of human passwords. This is really important for all kinds of automated processes and tasks, such as data processing jobs, backups, integrations, and so on. Secondly, service accounts enable granular access control. They allow the creation of very specific roles and permissions that are tailored to the needs of an application rather than to the profile of the user who wrote that application. And in this way, it's possible to specify exactly the right level of access for the app. This minimizes security risks by implementing the principle of least control. Using service accounts is an enhanced security practice. It isolates application access from user or developer access. Service accounts have their own credentials. These can be rotated, managed, and monitored independently of the developers of those systems. Finally, it's worth noting that the alternative to service accounts is having users specify their own identities in their apps. This is very unsafe. There is a lot of risk associated with the unnecessary exposure of user credentials, but also with the elevated privileges that user accounts might need in order to run specific apps. User accounts are usually authenticated using passwords which need to be changed frequently and may have to be deactivated if the user leaves the organization. Service accounts avoid these issues by using keys and in this way provide a stable and secure means for apps to access resources. The next type of principal could be a Google group. This is a named collection of Google accounts and service accounts. This is important. Service accounts can be members of groups, and a Google group is used to manage and facilitate communication and collaboration. Each Google group has a unique email ID, and this allows group members to send and receive emails collectively. A company, for instance, might create a Google group for its marketing team, and then all new joiners or existing employees who enter the marketing team will be made members of this group. This makes the marketing group able to perform operations and access resources without having all of the individual users have a larger set of permissions. It is also possible for entire Google Workspace domains to be principals in the IAM world. A Google Workspace domain represents a virtual group of all Google accounts created within that organization's Google Workspace accounts. Let's say, for instance, that an enterprise has the internet domain example.com. It would have a Google Workspace domain where all employee accounts ending in example.com are effectively allowed a certain level of access. This allows centralized management of email, docs, and other Google services so that any new or existing users who have accounts with that domain name can collaborate easily. The last kind of principle is a cloud identity domain. This is logically very similar to a Google Workspace domain. It too represents a virtual group of all Google accounts within an organization. However, we'd use a cloud identity domain primarily in cases where a company is not using Google Workspace, and so the users do not have access to Google Workspace apps such as Gmail, Google Drive, or Google Docs. Now that we have a good sense of the different types of principles supported by Cloud IAM, let's turn our attention to the other part of the picture, which is the access bit. Here, access can be specified using either role-based access control or access control lists. The only Google Cloud service that relies on access control lists is Google Cloud Storage, which also allows a role-based access control. Because ACLs are a lot more specialized, let's talk about them first. Unlike role-based access control, when you use an access control list, you can directly link permissions to users or service accounts. This does not have a role as a building block. So the ACL is effectively a set of rules to explicitly grant or deny permissions to individual users, groups, or entities based on their identity. Again, the only Google Cloud service that supports ACLs is Google Cloud Storage. Cloud Storage allows the use of ACLs to specify access to individual buckets as well as to individual objects. Each ACL consists of one or more entries. Each entry gives a specific user or group the ability to perform specific action. Each entry has a permission, which defines what actions can be performed, such as read or write, and a scope, sometimes called a grantee, which defines who can perform the specified action. For example, a particular user, bob@example.com. Let's now turn our attention to role-based access control. In contrast to ACLs, which have permissions for individual users or entities directly mapped to specific resources, role-based access control assigns permissions to roles, and those roles are then granted to users. So there's an additional layer of indirection. Role-based access control makes it easier to manage permissions across multiple resources. It's much more scalable and it simplifies administration. On the other hand, ACLs are better for detailed and resource-specific permissions. Within role-based access control, there are three types of roles, the simplest of which are the basic roles. These include owner, editor, and viewer. In general, the use of basic roles is discouraged in production environments because these roles, owner, editor, and viewer, are very broad. They include thousands of permissions across many Google Cloud services. Instead, we should go with the other types of roles, notably predefined roles. Predefined roles are roles created by the Google Cloud IAM service. These give much finer grained access control than the basic roles. They already have sets of permissions bundled together, and they greatly simplify the process of assigning rights to users, groups, and service accounts. These roles are created and maintained by Cloud IAM, and they cover most common use cases and admin tasks. Predefined roles are also maintained, so new predefined roles keep coming online. Here are some characteristics of predefined roles. The first is they are purpose specific. Each predefined role is designed to match a specific job function or task, such as managing VMs, accessing storage buckets, or monitoring system logs. Secondly, they allow for very granular permissions. As we shall see in a moment when we look at examples of such roles, there will be very specific predefined roles with very specific groups of permissions. And this makes them suitable from a security and compliance perspective. Organizations can ensure that the principle of least privilege is applied. On screen now, we are viewing one predefined role, and that role is roles/BigQuery.dataViewer. This role, of course, is a collection of permissions, and all of the permissions which this role has are listed below. These include BigQuery.datasets.get, BigQuery.datasets.getIAM policy, and so on. You can see now why we say that predefined roles have very granular and specific permissions associated with them. There's a very large number of predefined roles, but the IAM service also allows organizations to define their own set of permissions using custom roles. These roles are especially useful in cases where you have unique security or access requirements which go beyond standard permissions provided by the Google Cloud. Some points to keep in mind about custom roles. These allow administrators to specify exactly which permissions are included, so they have the highest level of tailoring possible for permissions. This is great for very fine-grained control over what users can and cannot do. Custom roles are the most flexible because they have the ability to perform operations across very different Google Cloud services. For instance, you might create a custom role where some permissions relate to BigQuery and others relate to Cloud SQL. There will be no predefined role which spans these two particular services. In return for all of this, you also have to keep in mind that custom roles are entirely your responsibility. They are not maintained by Google. So if new permissions, features, or services get added to the cloud, your custom roles will not be updated automatically. This is not true with predefined roles. They are constantly being updated by Google. We started this course off by understanding privileged access and the principle of least privilege. We learned how these concepts are critical in protecting against security threats. We also covered the fundamentals of confidentiality, integrity, and availability, which are essential components of a robust security framework. Next, we learned about various security measures to protect cloud resources. We compared on-premises security with cloud security and examined the different cybersecurity threats that organizations face today. We also explored the security infrastructure of Google data centers, gaining insights into how they ensure the safety and reliability of their services. Finally, we explored Google Cloud's product for role-based access control, namely the Identity and Access Management Service. We studied the different types of principals in Cloud IAM and the various roles they can assume. By differentiating between basic, predefined, and custom roles, we learned how to manage identities and access effectively, ensuring that only authorized users have access to sensitive information. In conclusion, we built a strong foundation in cloud security principles, measures to protect cloud resources, and identity and access management. We are ready to move on to the next course in this journey, Networks on Google Cloud. Network management on the cloud is very different from that in the on-premises world and involves very different tools and building blocks. Understanding Google Cloud networking technologies and their specific use cases enables organizations to build scalable, reliable, and secure cloud systems. In this course, you will learn about virtual private cloud on Google Cloud. You will explore shared VPCs and VPC peering for seamless communication between networks and VPNs for secure internet connections. Additionally, you will cover Cloud Interconnect, enabling private high bandwidth connections between your on premise network and Google Cloud. Next, you will study Chrome Enterprise Premium and examine BeyondCorp, Google's zero trust security model, and learn how Chrome Enterprise Premium implements the BeyondCorp model. You will also understand immutable infrastructure to ensure systems are not altered after deployment. You will learn about infrastructure as code as well as tools such as Cloud Deployment Manager and Terraform to manage infrastructure through code, enhancing automation and consistency. Finally, you will explore Cloud Armor to protect against DDoS and other cyber attacks. You will learn about cloud data loss prevention to identify and protect sensitive data. Additionally, you will integrate security practices into the operations workflow with SecOps, enhancing overall security posture. Let's turn our attention to networking on the Google Cloud. The basic building block, the abstraction on the Google Cloud is the VPC, or the Virtual Private Cloud Network. This term VPC on the Google Cloud refers to a virtualized network infrastructure. The VPC infrastructure allows enterprises to define and manage their own private network, and this in turn allows them to segment and isolate resources for both security and performance. Let's understand this VPC abstraction a little better. It's perfectly possible to have multiple networks, that is, multiple VPC networks within the same project. VPCs are global resources, which means that they span multiple regions within the Google Cloud infrastructure. That allows for various geographical locations to have compute or other resources which lie on the same VPC. Every project has something known as the default VPC. This is a pre-created VPC which comes out of the box with networking set up for initial deployments. This automatically includes subnets for each region, firewall rules, and routing configurations, and it allows users to quickly start deploying resources without needing to configure the network as the first operation that they do within a project. So let's add this information to our mental map of the VPC. VPCs are global and every project has a default VPC. Here we see a single project which has the default VPC and then two additional VPCs, VPC 1 and 2. VPCs are global, which means that they can span different regions. And then within each region, each VPC has something known as a subnet. So we can think of the subnet as the intersection of a VPC and a region. Of course, any resource that we provision has to exist in some region, and that in turn means that every resource that is provisioned on some subnet. Let's understand this subnet abstraction a little better. In the world of VPCs, there are no IP ranges. It's the subnets that have IP range partitions. So we should think of a VPC as a global container for network resources, and within that global container, we have individual subnets, and each subnet has an IP address partition range. The subnet itself behaves a lot like the network abstraction outside the cloud world. So each subnet is regional, it can span zones inside a region. So each subnet is confined to a single geographic region, but it can span multiple zones, that is, availability zones within that region. This leads to better availability and fault tolerance. And finally, every VPC network must have at least one subnet before it can actually be used. Now, it turns out that there are actually two types of VPCs, auto mode and custom mode. And with custom mode VPCs, we do not have pre-configured subnets for each region. More on that in a moment, but again, let's just reinforce the point that subnets are regional. This schematic block diagram shows that we have a VPC. Within the VPC, we have subnets corresponding to each region, and within this particular region, we happen to have two resources which are instantiated in different zones, A and B. Going back to the VPC abstraction, there are two types of VPCs, auto mode and custom mode. Auto mode VPCs are pre-configured and they automatically create subnets in each region with predetermined IP ranges. When a new region becomes available, a corresponding subnet is automatically created in that region. This makes it easier for users to deploy resources without needing to configure the network manually. This is ideal for users who don't want to concern themselves much with the networking at all. Custom mode VPCs are for users who want a lot more control and flexibility over the network configuration. Here, users can create and manage their own subnets with their own specific IP ranges in mind. VPCs have resources in different regions. Resources within a VPC will communicate using private IP addresses. This is true wherever they happen to be located, irrespective of their physical location. On the other hand, resources in different VPCs will communicate over the internet using external IP addresses. Once again, this is true irrespective of their physical location. Even if these two resources happen to be in the same region or even the same zone, they still will only communicate using External IP addresses. This is where the name VPC comes from. Resources within the same VPC communicate with private IP addresses. Resources on different VPCs communicate with external or public IP addresses. Now, just to be clear, there's some fine print here because these resources, which are in different VPCs, might have some other kind of communication, such as using VPC peering or Cloud VPN, in which case this statement might not be entirely true. But as applied to VPCs, this is generally true. Let's quickly enumerate some properties of the default VPC. Remember that this is the VPC that comes pre-created on every project. The default VPC is an auto mode VPC. It includes a subnet for each region. When new regions are created, subnets will automatically be added to all default VPCs. And finally, when resources are created within a project, by default, those resources will reside on this VPC. Now, we've referred to the concept of a firewall previously. As illustrated in this image, a firewall acts as a barrier between a private network and the internet. It filters incoming and outgoing traffic based on predefined security rules, allowing legitimate traffic from trusted sources to enter, but blocking potentially harmful traffic from attackers. It's interesting to note that every VPC is in effect a distributed firewall. What this statement means is that firewall capabilities are built into every VPC. This allows the specification of firewall rules at the VPC level. The VPC abstraction will enforce them across all resources within that VPC. These rules might define, for instance, what types of traffic are allowed or denied between different network segments or between the internet and the VPC. By specifying rules within the VPC, administrators can control inbound and outbound traffic. These rules are going to be applied on a per instance basis, meaning that they can be tailored to individual VM instances within the VPC. Finally, these firewall rules need not only apply to external traffic, they can also be used to regulate internal traffic, for instance, by controlling how different VM instances within the same VPC communicate with each other. Next, let's talk about how we can connect networks on the Google Cloud. Before we move any further, let's disambiguate the term network. Here, network might refer to a Google VPC or it might refer to an on-prem network. Let's first talk about the simpler case of connecting Google Cloud networks, that is, of connecting two VPCs. Here we have two options, shared VPCs and VPC peering. Before we describe them, let's first understand why we might want to connect two VPCs. Remember that a VPC is always in a single project. So one VPC exists in one project and only resources on that project can use that particular VPC. But what if we have multiple projects and we would like resources in these multiple projects to be on the same network? For instance, what if they are all part of the same larger product? That's where these two features of shared VPCs and VPC peering come in handy. Before we go into further detail, remember that shared VPCs need to be in the same organization. VPC peering will work even if the VPCs are in different organizations. That said, let's now talk in more detail about each of them. Let's start with the shared VPC. This is a feature which allows multiple projects within the same organization to share a VPC network. This setup can centralize the management and security administration of the network, and it allows for consistent configuration and better resource utilization across projects. By using a shared VPC, the different projects can securely communicate with each other while also benefiting from the unified network infra. To summarize, we use shared VPC across projects on the Google Cloud. In this particular feature, we have one VPC which spans multiple projects. Shared VPC will only work with projects that are in the same organization. And importantly, there are two types of projects. We've got to designate one host project. This is the project which owns the VPC network and the associated resources. In addition, there are service projects. These are projects that use the VPC network resources from the host projects. The shared VPC feature allows us to build some interesting architectures. Here is an example of shared VPC where we have got one host project that's towards the center right of the screen, and then we have two service projects A and B over on the left. Notice that within each of these service projects, we have corresponding VM instances. So we have instance A inside service project A and instance B inside service project B. What's important is that these two instances are on the shared VPC network, and that's why the internal IP addresses for those instances A and B have been specified within the host project. Finally, note that both of these IP addresses are internal, so here we have two different instances in two different projects which are still communicating with each other using internal IP addresses, and that is because of the shared VPC. Let's talk about the other way to connect two Google networks together, and that's VPC peering. VPC peering is going to work even if the two projects happen to be in different organizations. This is a great way to set up a network with high performance and low latency, and we avoid the need for additional gateways, virtual private networks, or external IP addresses. Here is a schematic block diagram where we show VPC peering in action. We have two projects, projects 1 and 2. Within these, we have the corresponding networks called Network A and Network B. Notice that there are peering routes in both directions. Both networks need to accept the peering connection for this feature to work. Now, VMs on these networks can communicate using internal IPs and over Google's network infrastructure. Let's hit some of the main points about this VPC peering feature. Like shared VPCs, VPC peering is used to connect two or more VPCs connected across different projects. But importantly, this time the projects need not be in the same organization. Resources on different VPC networks will be able to communicate using internal IP addresses, so traffic between instances on these peered VPCs will not hit the public internet. This increases security and reduces latency. It's also important to note that the resources on the network will use Google's infrastructure to communicate. So again, we are avoiding having to send traffic over the public internet while communicating between two Google networks which happen to be in different projects, even if those projects belong to different Google Cloud organizations. Next, let's move to the enterprise connectivity options on the Google Cloud. Enterprise connectivity here implies that we might be connecting VPC networks with each other or with other networks which might be on-prem or on other cloud platforms. We have two options here, Cloud VPN and Cloud Interconnect. Cloud VPN is easier to set up and is cheaper, but gives you lower bandwidths. Cloud Interconnect is more expensive and more complicated to set up, but it offers higher bandwidth connections and it avoids the public internet. With that high level distinction in mind, let's now talk about each in more detail. The VPN in Cloud VPN has the usual full form. It stands for Virtual Private Network. So Cloud VPN is a service that allows us to create a secure and encrypted connection over a less secure network such as the public internet. This way, users can send and receive data as if their devices were directly connected to a private network. We set up a Cloud VPN tunnel between an on-prem network or another cloud provider's network to our Google Cloud VPC network. This tunnel would be through an IPsec VPN connection. The traffic would be encrypted as it travels over the public internet. In terms of the key features of how Cloud VPN works, remember that we need two VPN gateways, one at the cloud network and one on the on-prem network. This is how the secure connection can be established. Traffic gets encrypted at the VPN gateway on the way out. It then hits the public internet and then comes back to the other end of the tunnel after traversing the tunnel where it has to be decrypted. This encryption and decryption process makes sure that while the data is on the public internet, data privacy and security are still maintained. It's worth noting though that for this encryption and decryption to work correctly, key interchange needs to happen. This key exchange is itself a fairly complex technical process. Cloud VPN makes use of something known as IKE version 2, that's the Internet Key Exchange Protocol version 2, and it also makes use of Diffie-Hellman for key exchange in order to establish a shared secret key without directly revealing it. Cloud VPN is fine for relatively low bandwidth connections, and it's also relatively easier and more lightweight to set up. The other enterprise connectivity option, which is more heavyweight, is Cloud Interconnect. This in effect establishes a high speed and low latency link between our on-prem network and our Google VPC, or this could also be a different cloud network and the Google VPC. In either case, this happens through dedicated physical connections. As you might imagine, this is a lot more expensive, but it also leads to far greater bandwidth and lower latency. Within Cloud Interconnect, there are three possible options. The first is for a direct physical interconnection. This is through a fiber optic cable directly from our on-prem data center to the Google Cloud infrastructure. This option is ideal for apps that require real-time data processing or very large data transfers. This is known as dedicated interconnect. Another option is called partner interconnect. Here, the connectivity occurs through a service provider. That service provider will be drawn from a list of providers who already have established physical connections to Google's cloud infra. This is not quite as heavyweight as dedicated interconnect. Also, it simplifies the setup process because the service provider takes the onus of managing the physical infrastructure and the connectivity. A third option, which is suitable if you have resources on a different cloud provider, is called cross-cloud interconnect. Here, the interconnection happens through a co-location facility where a dedicated physical link will be set up between the Google network and the network of the other cloud provider, which might be AWS or Azure. Potentially, other cloud providers could be connected as well. So, to summarize, across all of the different enterprise connectivity options on the Google Cloud, it's always going to be possible to set up dedicated and secure connections between an on-premise network and the Google Cloud resources. We are now going to talk about network security with BeyondCorp. This is a security framework developed by Google that serves as a practical implementation of the Zero Trust security model. BeyondCorp is a concept, but we can really think of it as being implemented using something known as Chrome Enterprise Premium, which itself is a subscription-based service. It includes a browser, that's Chrome Enterprise. This has several strong additional security features, and it's bundled with a service. This service plus the browser together implement the BeyondCorp framework. Let's quickly refresh our memory about what the Zero Trust model is in the first place. The Zero Trust model is a security framework based on the principle that no entity, whether inside or outside the network, should be trusted by default. This model contrasts with traditional security models which assume that everything within an organization's network could be trusted. The Zero Trust approach helps to mitigate risks associated with insider threats and unauthorized access. Zero Trust security is built on five pillars: strong identity verification mechanisms, strong device security, strong network security, including microsegmentation and implementation of least privilege access, application security, and finally, data security, that is, protecting sensitive data through encryption, tokenization, and strict access controls. The Zero Trust model leads to improved security by verifying each access request and limiting access based on the principle of least privilege. It reduces the attack surface by use of microsegmentation and strict access controls. It enhances visibility using continuous monitoring and analytics, which study network traffic and user behavior. All of these taken together lead to improved compliance and help organizations meet regulatory requirements easily. With this context in mind, let's understand BeyondCorp. This is a security framework developed by Google that shifts access controls from the traditional network parameter down to individual devices and users. BeyondCorp seeks to implement the Zero Trust security model and enable employees to work securely from any location without the need for a traditional VPN. It does so by treating every user and device as untrusted by default, whether they are inside or outside the corporate network. Next, let's outline some of the key principles of BeyondCorp. The first is identity-centric security. User and device identity are central to the security model. Each access request is authenticated and authorized based on user identity, device state, and contextual information such as location and time. Context-aware access, which means that access decisions are made dynamically, taking into account the context of the request. This includes factors like user identity, device security posture, location, and the sensitivity of the data being accessed. Device security is explicitly covered. Devices must meet specific security standards before they are allowed to access resources. This includes regular checks to ensure that devices are updated, compliant with security policies, and free of malware. Granular access controls are used in order to grant access on a need to know basis. BeyondCorp enforces least privilege access and ensures that users and devices only have the minimum necessary permissions required to perform their tasks. Centralized policy enforcement ensures that security policies are centrally managed and enforced across the entire network. This ensures consistency in access controls. Recently, BeyondCorp has been rebranded as Chrome Enterprise Premium. Chrome Enterprise Premium is a subscription based service. It adds security features, in fact, very strong security features, to the Chrome Enterprise browser. The Chrome Enterprise browser, with its additional security features, along with the additional services that come as a part of Chrome Enterprise Premium, together help to implement the Zero Trust framework. This product includes all of BeyondCorp's features as well as additional features, so it's also an enhancement. Chrome Enterprise Premium is now Google Cloud's Zero Trust solution. It enables an organization's workforce to access web applications securely from anywhere without the need for VPN and without the fear of malware, phishing, or data loss. By using Chrome Enterprise Premium, you can manage access for apps on the Google Cloud, other clouds on-prem, and define and enforce access policies based on user, device, and other contextual factors. Chrome Enterprise Premium has a couple of objectives. The first is comprehensive threat and data protection for enterprise devices, and the second is advanced access controls for secure system protection. In practical terms, this means that there are features included to protect enterprises from exfiltration risks such as copy and paste. Data loss protection is built into the browser, and this also helps to prevent malware from getting onto enterprise managed devices. This also includes richer access controls to protect access to secure systems by using the context of an end user's request to ensure that each request is authenticated, authorized, and as safe as possible. The idea behind Chrome Enterprise Premium, which until recently was known as BeyondCorp Enterprise, is that employees, contractors, and partners all can access the Google Cloud using Chrome. Now, threat and data protection are built into the browser. However, the protections are not merely on the client side or on the browser. There are also network protections, for instance, the use of proxies to protect the traffic over the internet. The Google Cloud is also leveraged to enforce access policies based on identity and context. And once all of these steps have been undertaken, then the user is able to access internal apps hosted on Google Cloud as well as other clouds, SaaS apps, and internal web apps hosted on-prem. Some common use cases for Chrome Enterprise Premium include enabling access for non-employees without requiring a VPN, provided that they meet minimum security standards. Another is to allow personal device data access, again for non-employees, provided that they meet a minimum security posture. The prevention of employees copying and pasting sensitive data into emails or saving data into personal storage solutions like Google Drive. And finally, restricting the access to key systems. So, for instance, only enterprise managed devices might be allowed to access key systems, and gate access might be based on a user's physical location. Next, we are going to talk about Google tools such as Google Cloud Deployment Manager, Cloud Build on Google Cloud, and also Terraform on Google Cloud. We shall see how all of these tie into the idea of enhancing security with immutable infrastructure. Let's begin by defining that term. Immutable infrastructure refers to a practice where infrastructure components such as servers or virtual machines are never modified after they are deployed. Instead, any changes or updates simply require the creation or deployment of new instances while the old ones are decommissioned. This approach of immutable infrastructure ensures consistency, it reduces configuration drift, and it increases security by preventing unauthorized or unintended modifications. Immutable infrastructure is closely tied to the idea of infra as code because it's usually achieved using automation and infra as code tools. Immutable infrastructure has several benefits, the first of which is consistency and predictability. With immutable infra, there is less risk of configuration drift where servers deviate from their intended configuration over time. All instances are consistent and predictable. Another aspect of the predictability is the reproducibility. Automating the provisioning of infra allows you to recreate the same infra environment reliably, reducing discrepancies between development, testing, and production environments. Immutable infra leads to improved security in a couple of ways. For one, it reduces the attack surface because the infra components are not changed after deployment, so there's less chance of unauthorized change. Likewise, configurations that could introduce vulnerabilities are unlikely to be introduced via any modifications. Because immutable infra is usually implemented using automated tools, security policies can also be applied consistently across all infra components. This ensures compliance with security standards and reduces scope for human error or bad intent. A third benefit is faster recovery and updates. For instance, it's possible to have rapid rollbacks in the case of a security incident or a failure. Immutable infra will allow for fast rollbacks to a known good state by redeploying the infra from a secure predefined image. Updates are also streamlined because no update contains modifications. Updates will only replace existing infrastructure with new updated instances. This makes the updates simpler and reduces potential risks associated with in place updates. A final benefit is enhanced monitoring and auditing. First, via immutable logs, automation tools will generate immutable logs for audit purposes, and this in turn generates a clear and unalterable record of changes and deployments. It's also possible to implement continuous monitoring. These can assess the health and security posture of the infrastructure, ensuring that deviations or anomalies are promptly detected and addressed. Immutable infrastructure is essentially an idea or a paradigm. Implementing or setting up immutable infrastructure comes down to two implementation techniques: automation and the use of infra as code. Automation involves using tools and scripts to perform repetitive tasks, and in this context, those repetitive tasks manage the deployment, configuration, and scaling of infra components. Automation tools will also enforce security policies, perform continuous monitoring, and automatically handle recovery and updates. Continuous integration and continuous deployment, that is CI/CD pipelines, are a part of this automation. By automating the build, test, and deployment processes, CI/CD pipelines ensure that code changes are integrated and deployed consistently and quickly. Another pillar of the implementation of immutable infra is IAC, or Infrastructure as Code. This is a practice where infra is defined and managed using code, allowing for version control, repeatability, and automation. Tools like Terraform, Cloud Deployment Manager, and so on enable the provisioning and configuration of infra components based on predefined templates or scripts. IAC makes it easier to create immutable infra by ensuring that deployments are consistent and reproducible. This makes it easier to manage infrastructure in a controlled fashion. Let's elaborate a little more on the very common acronym CI/CD. CI stands for continuous integration. This is the practice of automatically integrating code changes from multiple contributors into a shared repo several times a day. Each integration will trigger an automated build and test process to detect errors early and ensure that new code changes do not break existing functionality. CI, that is continuous integration, helps developers identify and address issues quickly, improving the overall quality of the software. Then we come to CD. This, it turns out, actually has a couple of different full forms. One is continuous deployment. This is the practice of automatically deploying every code change that passes the automated tests to a production environment. Continuous deployment ensures that software is always in a releasable state. It enables a rapid delivery of new features and bug fixes to end users. Continuous deployment minimizes the manual steps required to release software and reduces time to market. Then we come to the other CD. This is continuous delivery. This is very similar to continuous deployment but with one additional manual approval step before deployment to production. This approach ensures that code changes are automatically built, tested, and prepared for a release to production, but a human decision is required to actually initiate the deployment. Continuous delivery provides a balance between automation and control. It ensures that the software is always ready for deployment, but it allows teams to maintain oversight over the final release process. Now that we've set the table, let's talk about tools on the Google Cloud for immutable infra. The first is Google Cloud Deployment Manager. This is an infra as code tool that allows users to define, deploy, and manage Google Cloud resources through configuration files. It uses YAML, Python, and Jinja 2 templates to describe the desired state of the infra, making it easy to automate provisioning and management of cloud resources. It ensures consistent and repeatable deployments, reduces the risk of manual error and configuration drift. It also integrates seamlessly with all of the other Google Cloud services. You can use Cloud Deployment Manager to create really complex environments. For instance, you might define and deploy a multi-tier web app specifying resources like VM instances, load balancers, and databases all in a single config file. By running a single command, Deployment Manager will provision all of these required resources, ensure that they are correctly configured and connected, and fail gracefully if a problem arises. Terraform on Google Cloud is an open source IAC tool. It allows users to define, provision, and manage Google Cloud resources using declarative config files. Just to be absolutely clear, Terraform on Google Cloud is not a managed service. Rather, this involves running Terraform, which itself is the open source tool developed by HashiCorp, on the Google Cloud platform. So to use Terraform on the Google Cloud, you would install and configure Terraform on any server of your choice. You would define your config file written in HCL, and then Terraform would make use of Google Cloud Provider plugins in order to interact with the GCP APIs and implement your configuration file. These configurations are written in a language called HCL. Because Terraform is very widely used, there is a wide acceptance of HCL. Users can describe the desired state of their cloud infra, including compute instances, networking, storage, and other services. Just like Deployment Manager, Terraform ensures consistent and repeatable deployments by applying these configurations to create and manage resources. Also relevant in this context is Cloud Build on Google Cloud. This is a fully managed CI/CD platform that automates the build, test, and deployment of applications. It allows developers to create custom workflows using simple YAML config files. It enables the automation of various tasks like the compilation of code, running tests, and deploying to different environments. Cloud Build integrates seamlessly with other Google Cloud services as well as with GitHub and GitLab. It also supports a wide range of programming languages and app frameworks. We will now discuss two Google services, Cloud Armor and Cloud Data Loss Protection. Let's set the table by first defining a distributed denial of service attack. This is a malicious attempt to disrupt the normal traffic of a targeted server, service, or network by overwhelming it with a flood of internet traffic. The usual procedure here is for the malicious party to try and take over multiple compromised devices distributed across various locations. That's where the distributed in the name comes from. Then these compromised devices will generate an excessive number of useless requests, send these to the target, and then that will overwhelm the target, causing it to slow down, crash, and thereby become unavailable to legitimate users. And in this way, the legitimate users are denied service. DDoS attacks are often launched using botnets, which are networks of infected devices that are controlled by the attackers. And this control usually happens without the knowledge of the owners of those devices. And it is in order to prevent such attacks that Google has Cloud Armor. This is a Google Cloud security service designed to protect apps and websites from various types of cyber threats, which include DDoS attacks as well as other web-based attacks. Cloud Armor has a robust set of tools for configuring and enforcing security policies to safeguard your apps, whether those apps are deployed on the cloud, in a hybrid deployment, or in multi-cloud architectures. Let's talk through some key features of Cloud Armor. The first is DDoS protection. Cloud Armor helps defend against large-scale DDoS attacks by absorbing and then dispersing the traffic across Google's global infra. A second feature is that Cloud Armor includes a web application firewall. This allows you to create custom security policies to block or allow traffic based on rules that you define. These rules can be used to protect against common web application vulnerabilities such as SQL injection and cross-site scripting. Cloud Armor comes with a predefined set of security policies. These can be easily applied to your apps and thereby provide immediate protection against known threats and attacks. These predefined security policies would effectively be pre-configured rules for the web application firewall. They'd have dozens of signatures that are compiled from open source industry standards. Each signature corresponds to an attack detection rule in the rule set. Finally, it also offers geo-blocking and rate limiting. That means that you can block traffic from specific geographic regions or IP addresses, and you can also set rate limits to control the amount of traffic from individual IP addresses. Taken all together, these features make Cloud Armor formidable protection against DDoS and other attacks. OWASP is a famous organization. OWASP is short for Open Web Application Security Project. The OWASP Top 10 is a very widely used list of the most critical web application security risks. It serves as a guideline for developers and security professionals. This list includes issues such as injection, broken authentication, cross-site scripting, and others. This OWASP Top 10 is regularly updated, and Cloud Armor comes with pre-configured web application firewall rules for the OWASP Top 10. The Cloud Armor service serves at the network edge. As we can see in the schematic block diagram, when a user request comes in over the internet, it is met at the network edge by Google Edge POPs or points of presence. And it is here that we effectively have our IP address allow list and deny list. This is also where the load balancers are situated. The net effect of this is that malicious traffic is cut off right at the edge of the Google Cloud infra. Next, let's switch gears and talk about another Google Cloud service, that's Cloud DLP, that's short for Data Loss Prevention. This is a managed service that's designed to help enterprises discover, classify, and protect sensitive information across their cloud environments. Cloud DLP is actually a part of a suite of services together called Sensitive Data Protection. Other services in Sensitive Data Protection include data discovery, inspection, de-identification, data risk analysis, and the DLP API. Let's discuss some of the key features of Cloud DLP. The first is automated sensitive data discovery and classification. Cloud DLP automates this discovery process by profiling every BigQuery table and column. It gives you a comprehensive overview of your data landscape. It also has a number of predefined detectors. These help to detect common types of PII or other sensitive data. Alternatively, you can also create your own custom types. It's also possible to adjust detection thresholds and set detection rules for your specific use case. Let's quickly outline some common use cases of Cloud DLP. Cloud DLP is great for sensitive data intelligence needed to conduct security assessments. It can also be used for de-identification, masking, tokenization, and bucketing. DLP can also be used for masking of data, which is going to go into the training of AI/ML workloads. DLP is one part of the Sensitive Data Protection Suite. This is a fully managed service with many capabilities. Let's quickly talk about some of the others. Sensitive Data Discovery. You can use this to discover, scan, and monitor your entire data warehouse. A second is Storage Inspection. This offers targeted, focused inspection so that you can find data elements in Google Cloud storage systems for investigations or dealing with high-value unstructured data such as chat logs. Hybrid inspection is similar, but it works with storage systems outside the Google Cloud. Content inspection, which is synchronous stateless inspection on data from anywhere in near real time. And finally, there's content de-identification, which can be used for masking, tokenizing, and de identifying in near real time. Both content inspection and content de identification can be integrated into custom workloads, applications, and pipelines. Let's understand the term security operations, aka SecOps. This term refers to an approach that integrates security practices into the operations of IT and dev teams to ensure continuous monitoring, threat detection, and rapid response to security incidents. The idea is that just as DevOps serve to bridge the gap between development and operations, SecOps will serve to bridge the gap between security and IT operations. SecOps teams have a number of functions as envisioned in this approach. The first is to reduce the risk of data breaches. They also work to prevent or mitigate system outages and to prevent and mitigate other security incidents. Then they also identify and manage vulnerabilities so that they are always scanning the threat environment. And two other key aspects of their remit include log management, so the analysis and inspection of logs, and incident response. This is a core responsibility of SecOps teams. By integrating security into the day to day of IT operations, enterprises can reduce the risk of data breaches. Better availability via the CIA triad also results in increased uptime. Compliance becomes simpler because it's now easier to demonstrate to regulators and other stakeholders that regulations are being complied with. And finally, because of the overhead of security incidents is likely reduced, employee productivity goes up as well. All in all, this leads to a better and more productive work environment all around. In order to enable SecOps teams to live up to their full potential, the Google Cloud offers the Security Command Center. This is a comprehensive security and risk management platform that's designed to provide visibility, monitoring, and protection for Google Cloud environments. The Security Command Center has three editions. Standard Edition, this is for Google Cloud environments with fairly minimal security requirements. Premium, which is for customers who need pay as you go billing, and then the Enterprise Edition, which can work to protect Google Cloud, AWS, as well as Azure. So it provides protection in a multi cloud environment. It's also relevant here to talk about the acquisition of Mandiant, which happened in 2022. Mandiant is a renowned cybersecurity firm known for its expertise in threat detection, incident response, and cyber intelligence. It was acquired by Google in 2022 and is now part of Google Cloud. The Security Command Center heavily relies on Mandiant's technologies for threat and vulnerability detection. Let's talk about some of the key features and use cases of the SCC. Comprehensive threat detection is one of the primary use cases. SCC utilizes built in as well as integrated Google Cloud services to scan logs, containers, and VMs for threat indicators. Real time alerts allow analysts to quickly detect, investigate, and respond to potential threats. It integrates with tools like event threat detection and container threat detection. SCC provides vulnerability management by automatically scanning resources for software vulnerabilities, misconfigurations, and security issues that might expose the organization to attacks. It provides detailed info on each detected vulnerability, including associated CVE records and impact assessments from Mandiant. CVE is short for Common Vulnerabilities and Exposures, and a CVE record has information about each vulnerability in terms of a CVE ID, a vulnerability description, and most importantly, something known as a CVSS score. CVSS is short for Common Vulnerability Scoring System. The CVE record also includes patch information so that it becomes easy to patch or mitigate this particular vulnerability. In addition, impact assessments from Mandiant are also included in this feature. High severity vulnerabilities will trigger automatic case creation to prioritize and track remediation. The Security Command Center also helps with security posture management. It assesses and reports on security configurations of cloud resources and compares them against common industry compliance standards. It will map misconfiguration detectors to compliance controls and give detailed insights into your compliance status. The SEC has integrated case management, so it offers integration with ticketing systems such as Jira or ServiceNow and allows security teams to assign owners, track the progress of investigations, and so on. Here is a schematic block diagram of how the Security Command Center enterprise works. Over at the bottom, we see different cloud platforms such as AWS, Google, and Microsoft. Above this, we see what Google refers to as a planet scale data lake. This includes Google's extensive security fabric and that large data lake to analyze cloud data, that is unstructured data. And also notice there Google Gemini. So a lot of this analysis is performed leveraging artificial intelligence. The insights from Google Gemini, that is the AI generated insights, are combined with mandated threat intel and feed into a continuous risk engine. That in turn feeds into the remediation module, which has actions which range from proactive to reactive. The proactive actions serve to set the enterprise posture, and the reactive are effectively threat mitigation strategies. We started this course off by learning about virtual private cloud on Google Cloud. We explored shared VPCs and VPC peering, which allow for seamless communication between VPC networks, and VPNs, which provide secure connections over the internet. Additionally, we covered Cloud Interconnect, which enables private high bandwidth connections between your on premises network and Google Cloud. Next, we learned about Chrome Enterprise Premium and examined BeyondCorp, Google's zero trust security model, and learned how Chrome Enterprise Premium implements the BeyondCorp model. We also explored the concept of immutable infrastructure, which ensures that systems are not altered after they are deployed. We also covered infrastructure as code as well as tools such as Cloud Deployment Manager and Terraform. Finally, we explored Cloud Armor, a service for protecting against DDoS and other cyber attacks. We learned about Cloud Data Loss Prevention, a tool for identifying and protecting sensitive data. Additionally, we combined our knowledge of security and operations into SecOps, integrating security practices into the operations workflow to enhance overall security posture. In conclusion, we built a strong foundation in VPC, secure connections, enterprise solutions, immutable infrastructure, and advanced security measures. We are ready to move on to the next course in this journey, compliance and operations on Google Cloud. Google has comprehensive trust principles and support for various international standards and regulations related to trust and safety. Enterprises can also leverage Google Cloud support and services to ensure sound cloud cost management and operations. In this course, you will learn about the Google Trust Principles and data sovereignty considerations, ensuring data security and compliance with international regulations. You will explore Google Cloud compliance resources to understand the guidelines and tools available for meeting compliance requirements. Next, you will study financial governance on the cloud, including best practices for managing cloud finances. You will learn about Google Cloud resource hierarchies to effectively organize and manage resources. Additionally, you will explore cost management tools on Google Cloud, such as the Google Cloud Billing Calculator, to control cloud consumption and optimize resources. Finally, you will build knowledge in cloud reliability with DevOps and basic reliability concepts in cloud environments. You will learn about observability tools on Google Cloud, such as logging, monitoring, profiling, tracing, and error reporting. Additionally, you will explore Google Cloud customer care, support services, and the lifecycle of a support ticket. Let's talk about Google's trust principles. Google uses these principles in designing and building its cloud and other products. The trust principles focus on ensuring user privacy, security, and transparency in all of its services. You own your data, not Google. So users retain ownership and control of their data, and Google provides options to access, export, delete, and manage permissions on the Google Cloud. Google does not sell customer data to third parties. This ensures data privacy. Google Cloud does not use customer data for advertising, so it's kept confidential. All customer data is encrypted by default. This is to protect it against unauthorized access. Google guards against insider access to your data. It has strict security measures to prevent unauthorized employee access to customer data. Google never gives any government entity backdoor access. Government entities can only access data with proper legal authorization. Google's privacy practices are audited against international standards. It also provides transparency reports so that users get insight into data protection efforts. These principles feed into Google's commitment to secure data. Google processes data according to data protection agreements, and it explains its approach to security. It outlines its policies on government requests using transparency reports. These transparency reports are detailed documents. They provide insights into how laws and policies impact privacy, security, and access to information. They inform users about the frequency and nature of government and corporate requests for data, the removal of content, and the enforcement of Google's policies. Google's aim in publishing these reports is to increase accountability and inform the public about how Google responds to government requests and actions. These reports are available at the URL you see on screen now, transparencyreport.google.com. Next, let's understand two important data-related concepts: data sovereignty and data residency. Data sovereignty refers to the legal principle is governed by the laws and regulations of the country in which it is collected. This principle emphasizes that data should be governed by legal frameworks of the location where it originates. Many countries have implemented data sovereignty laws or regulations which dictate where that data must be stored, who can access it, and under what circumstances. Just to be clear, there are some Google Cloud training materials which refer to data sovereignty as the legal principle that data is governed by the laws and regulations of the country in which it is stored. This, I believe, is incorrect. It actually should be the laws and regulations of the country where the data is collected or where it originates. Another contrasting principle is data residency. This describes the physical location where the data is stored or processed. Some jurisdictions mandate that data, especially sensitive personal information, should be kept within national borders. For example, Russia has data privacy legislation which requires that companies with employees in Russia manage master personal information in a Russian data center. Many jurisdictions have laws or regulations which try and square the circle between data sovereignty and data residency. For instance, the European Union has the GDPR, or the General Data Protection Regulation. It applies regardless of where websites are based, which means that it must be followed by all sites which have any European visitors, even if they don't specifically market goods or services to EU residents. GDPR ensures that individuals have control over their personal information. As a user of the Google Cloud, you can use regions to control the storage location of your data. All Google services are available across multiple regions, and there are choices that a user can make with regards to data on virtual machines, cloud storage buckets, and BigQuery. These services can be configured so that they only store data within a region of your choice. The Google Cloud supports different diverse regional options. For instance, in Europe, we have countries such as the UK, Belgium, Germany, and so on. There are also multiple locations within the US for data that needs to reside there. By choosing the appropriate region, your enterprise can be compliant with service-specific terms. Google ensures that your data is stored exclusively within that particular selected region, and this guarantees that your data remains within the specified jurisdiction. In this context, it's also worth talking about constraints and configurations. Google Cloud provides organization policy constraints that allow administrators to enforce policies on where the data can be stored. By setting these constraints, an organization can prevent accidental storage of data in non-compliant regions. This feature can be coupled with the Identity and Access Manager configuration options. These policies can help control access to resources based on their geographic location. IAM settings will ensure that only authorized users can configure and access data in specific regions. This further safeguards data from being stored in unintended or unauthorized locations. Google Cloud has VPC service controls. These provide additional security for your data because they allow you to define a security perimeter around your Google Cloud resources. This can help prevent data exfiltration because it ensures that only authorized services and users can access and interact with your services, and that too within the perimeter. VPC service controls work by creating boundaries around your VPC networks and applying access restrictions to APIs. VPC service controls protect against unauthorized network access by ensuring that only authorized VPC networks can access resources. They prevent data exfiltration by malicious insiders or by compromised code that might be trying to access resources which are outside the defined perimeter. VPC service controls serve to restrict external data transfers because they can be used to block operations like copying data to external or public resources. They act as an extra layer of security and provide defense in depth because even if an organization has misconfigured IAM policies, the VPC service controls will deny access to unauthorized networks. VPC service controls help with monitoring and analyzing access. They can be used in something known as dry run mode in order to monitor access requests without blocking them. This helps to identify and analyze traffic patterns and create honeypot perimeters to detect malicious probing attempts. A honeypot is a decoy system designed to attract and trap cyber attackers. It mimics a real system but does not contain any critical data. So, a honeypot perimeter is a perimeter around the actual security perimeter where honeypots are placed. These serve as early warning systems. They detect and deflect attackers before they breach the actual network defenses. In this context, it's worthwhile reiterating some features of Cloud Armor. Here is an architecture diagram of how Cloud Armor works. We have a user with a user request which enters the Google Cloud via the internet. The important point is that Cloud Armor runs on the network edge. The incoming user request hits the cloud edge and is picked up by a Google Edge POP or point of presence. It is at this point that Cloud Armor has its rules, for instance, IP address allow lists or deny lists. And what's important here is that Cloud Armor also allows us to set traffic locations for our external load balancer. So we can specify geographic regions from which traffic is allowed and thereby block potentially malicious traffic from unauthorized or high risk locations. By enforcing location based access control, Cloud Armor helps protect your applications against distributed denial of service attacks. Next, let's turn to support that Google provides to compliance by region and by industry. The term compliance is used in a lot of different contexts. Let's just level set. Compliance here refers to adhering to laws, regulations, and standards, as well as ethical practices set by regulatory bodies and industry standards. Google has a great compliance resource center. This is a comprehensive hub which provides information on Google's compliance docs, certifications, and controls. The documentation here maps Google's security and privacy measures to global standards, and it makes it easy for users of the Google Cloud to validate adherence to industry practices. It has compliance offerings organized by region and industry and is subject to independent verification. Google undertakes regular independent audits and certifications and has attestations and reports to demonstrate compliance with different international standards. It includes a resource center and featured papers with valuable documentation and guides on regulatory considerations, data protection, and specific industry insights such as telecom. Here are a couple of examples of region-specific compliance. In the US, for instance, we have FedRAMP, or the Federal Risk and Authorization Management Program. This is a US government-wide program that standardizes security assessment, authorization, and continuous monitoring for cloud products and services. FedRAMP compliance is mandatory for cloud service providers working with US federal agencies. It's designed to ensure that cloud services used by the federal agencies meet stringent security requirements. The European Union has the GDPR, or the General Data Protection Regulation, which, as we've already briefly discussed, is a comprehensive data privacy law. Next, let's take a couple of examples of industry-specific compliance. In the payment card industry, PCI DSS is a set of security standards that is designed to ensure that all companies that process, store, or transmit credit card information maintain a secure environment. PCI DSS has been established by major credit card companies such as Visa, MasterCard, and American Express. Adherence to PCI DSS is mandatory for any organization handling payment card transactions. HIPAA, the Health Insurance Portability and Accountability Act, sets national standards for protecting sensitive patient health information in the US. HIPAA aims to protect patient privacy and secure health information from unauthorized access and disclosure. It requires healthcare providers, insurers, and their business associates to implement stringent security measures. To help organizations comply with all of these different standards, the Google Cloud has Compliance Reports Manager. This centralizes access to various compliance reports, attestations, and certifications, and it helps organizations in meeting regulatory and industry standards. Let's take a brief segue to the Google Cloud Console in order to check out for ourselves the Google Compliance Center and the Compliance Reports Manager. This will also give us a good sense of the support that the Google Cloud provides for region and industry specific compliance. We start by navigating to the URL https cloud.google.com/compliance. This is the Compliance Resource Center. Let's scroll through this site slowly so that we get a sense of what it has to offer. Here, towards the center of the screen, we note compliance offerings by region and by industry. Then there are featured papers, industry spotlight on a specific industry, that's telecom, and then compliance offerings by category. We get a sense here of just how exhaustive this list of laws and regulations and frameworks is. We see that there's a long list of jurisdictions, and we can click through into each one of these for more details. Then, once we've oriented ourselves with this page, let's scroll back towards the top where we have compliance offerings by region and by industry. To begin with, let's click on the USA. This is listed under the regions. That opens up a new page where we have all of the compliance offerings that are relevant to the United States. And scrolling down, we see that this is a really comprehensive list. We see here the CCPA, COPA, and scrolling down, we notice many familiar names: FedRAMP, FINRA, HIPAA, and scrolling even further down, we note that this is just page 1 out of 3. In any case, let's now scroll back to the top where we have various filter options. This is a separate set of filters, so we open up the country filter option, scroll down to the bottom, and check the box next to the United States. We can quickly verify for ourselves that in the regions box, the USA is now checked. Next, let's switch to the industries and drill down into industry-specific regulation within the United States. So we check the box next to government and public sector, and the list of regulations now updates. For instance, we see FedRAMP. We can also drill down further by focus area. So let's check the box for security, and we see right away that we now have the ISO IEC 27000 family appear here. Let's click through on the Learn More option. Towards the top of that page, we see details of what this standard is all about. And as we scroll further down, we get details of Google Cloud services that are in scope. And we see here there are headings for Google Cloud, Google Workspace Admin SDK, Chrome, Apigee, and Communications. Let's expand the dropdown next to the Google Cloud, and we note that there is a very long list of Google Cloud products that adhere to this standard. In fact, for all intents and purposes, Google Cloud as a whole adheres to the standard. This explains why using services of the hyperscalers like Google Cloud help organizations with their compliance efforts. It helps if large swaths of your infrastructure are already compliant. We are done exploring regulations for the USA. Let's switch back to the original URL, close the other tab, and now click on Financial Services. Previously, we had clicked on the USA under Compliance Offerings by Region. Now we are clicking on Financial Services under Compliance Offerings by Industry. This opens up a new tab yet again, and once again we are able to filter by the types of compliance offerings that we are interested in, but this time they all apply to the financial services industry. Let's use the filter functionality. We open up the focus area drop box, scroll towards the top and click privacy and security. This will now display all compliance regulations or standards related to the financial services industry and where the focus area is privacy or security. Let's now go back to the filtering functionality, and this time we check the box next to EU members. As a quick check that this is showing correct results, we scroll down and verify that the famous GDPR does indeed appear here. In similar fashion, let's find PCI DSS. We scroll back up to the top, get rid of the filter for EU members, and then under countries, we select global. For that, we'll have to scroll towards the top. Once we make the change and scroll down, we find PCI DSS listed here. And of course, we can now click through and get a list of all of the different Google products that are compliant with this standard. For that, we've got to scroll down and expand Google Cloud. And here is that very long list of Google Cloud services. That does it for the Compliance Resource Center. Let's quickly switch over and check out the Compliance Reports Manager. The URL, it's visible in the browser address bar, https cloud.google.com/security/compliance/compliance reports manager. You can also just search for this on Google and then click through into the first hit. In any case, here we are at the Compliance Reports Manager. This is a good way to get the latest compliance reports organized nicely by compliance standard, report type, product area, and last audit. Here, for instance, we see a row corresponding to C5 2020. It's an audit report for Google Workspace, and it's dated 9th June 2024. Once again, there's a lot of information here, so we might want to scroll back up towards the top and there filter by industry, region, report type, product area, and so on. We quickly do a search where in industry we have financial services, in region we have global, and in product area we have Google Workspace. As you can see, this is a great way to drill down into the latest compliance reports, and it's searchable and filterable as well. Let's now talk about the importance of financial governance on the cloud. Because cloud computing is a new paradigm for many enterprises, financial governance has a renewed importance. Let's understand some of these aspects, starting with the need to prevent budget overruns. Cloud resources are very easily accessible and they can be scaled up or down rapidly. Without proper control, this can lead to significant budget overruns. Financial governance is required to ensure that strict policies and monitoring systems are in place to track and control spending in real time and prevent unexpected costs. Financial governance also needs to be about enforcing accountability, for instance, by assigning cost centers and budgets to different teams and projects within an organization. This accountability will ensure that each team is responsible for managing their own cloud spending. It's also important to optimize resource allocation. Seemingly small choices in cloud configurations can lead to large differences in costs and budgets. Finally, it's also important to enhance predictability and planning. Financial governance provides the framework for better predictability in cloud spending, and it allows organizations to forecast expenses accurately. In the context of the cloud, financial governance faces some rather specific issues. The first has to do with the transition between capital expenditures and operating expenses, CapEx versus OpEx as these are known. Migrating to the cloud involves shifting from a CapEx based model where large upfront investments are made in hardware and infra to an OpEx based model where costs are incurred on a pay as you go basis. This transition can be challenging. It requires a change in budgeting and financial planning practices, as well as a more flexible and dynamic approach to managing expenses. The ease of access and use of cloud resources also adds a challenge here. Cloud resources can be rapidly provisioned, and without proper governance, this can lead to uncontrolled usage and budget overruns. Organizations need to implement strict access controls, usage monitoring, and cost management practices. The cloud also poses different challenges in terms of visibility and control. On-prem environments typically offer more straightforward tracking and control over resource usage and costs. On the cloud, the decentralized nature of resources and the complexity of cloud pricing models can make it difficult to maintain visibility and control. Properly managing cloud costs in an organization has aspects related to people, process, and technology. Teams need to be trained on using cost management tools and understand the cloud billing models. Process needs to be updated in order to adapt to the dynamic and scalable nature of the cloud, for instance, by adding continuous monitoring, automated cost controls, and regular cost reviews. Technology needs to be leveraged as well because effective cost management on the cloud relies on the use of advanced tools and techniques for monitoring, analyzing, and optimizing spends. Let's talk about the people who actually manage cloud costs in an organization. In a small organization, that might be just one person who wears multiple hats, managing both cloud infra and associated finances. This same individual is responsible for budgeting, procurement, and tracking optimization. This leads for streamlined decision making and quick adjustments to cloud spending. Of course, this does not scale well, and that's why in larger organizations, finance teams are required. The dedicated finance team will typically handle financial planning and advisory roles. Such a team will typically monitor cloud spend on a daily, weekly, or monthly basis due to the complexity and scale of the cloud operations. The role played by tech teams is very important here. They ultimately know what cloud resources are actually needed, how these resources are to be managed efficiently, and how their usage can be optimized. Business teams also play a role here because they need to focus on how cloud resources align with and support business objectives. They need to ensure that the cloud investments are driving true business value and contributing to strategic goals. So, business teams ought to communicate their needs and priorities clearly to the finance and the tech teams. What jumps out is the need for collaboration across teams, including finance, technology, and business. Finance teams must understand technical requirements and constraints. Tech teams need to be aware of budget limits as well as business objectives, and business teams need to articulate their goals and expectations very clearly. All of these considerations lead many enterprises to establish what's known as a cloud center of excellence. This is a centralized hub of expertise where experts from all of these domains, finance, tech, and business, will collaborate. This leads to visibility and best practices. The central team within a cloud center of excellence ensures that there is comprehensive visibility into ongoing cloud spend and resource utilization. An important objective of a cloud center of excellence is aiding real time decision making. For instance, when expenses exceed planned budgets, this centralized group can quickly assess the situation, discuss trade offs, and implement corrective actions. This agility ensures that cloud spending remains aligned with business priorities as well as financial constraints. Next, let's discuss some of the many process related aspects of managing cloud costs. To begin with, there is the daily and weekly monitoring and analysis. This is important in identifying any unexpected spikes or changes in trend. It's also important to have regular financial reviews and chargebacks. These could be performed on a weekly or a monthly basis, and here the finance team should review cloud usage data, analyze spending patterns, and charge back costs to the appropriate teams. This ensures that each team is held accountable for their cloud consumption. In general, the process of strategic budgeting and forecasting becomes more important. It also needs to become more dynamic because of the change in capex and opex considerations. For instance, now budgeting should regularly involve updates on real time usage data and predictive analytics. There is now a much greater need for continuous optimizations and adjustments. The dynamic nature of the cloud means that plans may no longer remain valid for as long as they used to. In general, enterprises should foster a culture of accountability by holding each team responsible for their cloud usage and costs, and they also need to ensure cross group collaboration. Processes need to take into account the sensitivities of the different stakeholders. Let's move now to some of the aspects of how technology can be used to manage cloud costs effectively. The cloud platforms provide cost management tools which give much greater visibility into cloud costs than in the traditional on prem model. These can be used to instill a culture of accountability by tracking and reporting on cloud spending at granular levels. Automated reports and dashboards can also be constructed here to allow each team to monitor their own usage and costs. The cloud platforms also offer tools for cost control and cost reduction. For instance, they allow enterprises to set spending limits as well as alerts for potential overspending. All of these features should be leveraged. The hyperscalers also provide recommendations for cost optimization. These recommendations are getting steadily better through the use of AI and ML, and because the hyperscalers have had so much time and data to analyze usage patterns. So now these recommendations might include a right sizing resources, identifying underutilized services, and suggesting cheaper alternatives. All of these should be taken into account. Finally, enterprises should consider automating their resource management. Examples of this might include automated policies for starting and stopping instances, adjusting storage capacities, and using infra as code tools like Google Cloud Deployment Manager. All of these measures can significantly reduce manual intervention and associated costs. Cloud financial governance is very important, and that's why it's worth our while spending some time on specific best practices. The first is that we should identify who manages cloud costs. There should be clear ownership for cloud costs. This ideally should involve a mix of IT managers and financial controllers. Second, the enterprise should explicitly set up accountability and control mechanisms. Third, there should be a clear understanding of the differences between using invoices and using cost management tools. And cost management tools need to be leveraged to the fullest. All of this should be done on an ongoing basis so that there is a system to monitor and report costs regularly. Let's go through each of these in more detail, starting with step 1, identifying who manages cloud costs. Here, there's a need to establish clear ownership, ideally assigning a team which consists of both IT managers and financial controllers to oversee the cloud costs. Once there is a dedicated group responsible for managing and monitoring expenses, this in turn fosters a culture of accountability. This leads to the second of our best practices, which is all about establishing accountability and control. One excellent way of creating accountability is by defining ownership for cloud projects and then sharing cost views with the relevant departments and teams. It's also important to implement financial governance policies and permissions, which can be done by leveraging Google's tools to create multiple budgets and add alerts. A third key aspect is clearly understanding the difference between invoices and cost management tools. An invoice is just a document sent by a cloud provider to request payment. It provides a summary of the costs incurred over a specific period and details the amount owed by the customer. This is useful for financial accounting, but it offers no insights into why the costs were incurred or how they can be optimized. In contrast, cost management tools like those in the Google Cloud Console help to track, analyze, and optimize cloud spend. They provide granular data, uncover trends, and identify actions to control or reduce costs. Unlike invoices, cost management tools answer the why behind expenditures and support proactive financial governance. This is why cost management tools are so important, and we should make sure to use everything that the Google Cloud has to offer. There are comprehensive cost tracking and analysis tools, and these are a great tool for proactively managing costs on the cloud. They can help you set up budgets, create meaningful alerts, and monitor costs in real time. Once an enterprise has made the most of these cloud management tools, then it's time to monitor and report these costs on a regular basis. This requires, firstly, the setting up of regular monitoring and reporting, and secondly, a formal process to review those costs from time to time. In order to understand Google's cloud management tools, it makes sense for us to learn about cloud billing and the resource hierarchy. Cloud billing is a cloud service that helps organizations manage and track their cloud expenses. The cloud billing service can be used to analyze costs and trends. It has detailed reports and visualizations that help you understand your spending patterns, and you can use these in order to figure out what services are accounting for the bulk of your costs. Cloud billing is also a great way to monitor your costs, especially because it allows you to export your billing data to BigQuery and then use tools like Looker Studio for visualization. This way, you can set up regular monitoring and alerts and real time dashboards to keep tabs on rising costs. Cloud billing is also a great way to optimize costs. You can create budgets, set up spending alerts to keep cloud costs in check, and automate cost control measures with the Budgets API. You could use this API, for instance, in order to automatically adjust quotas to prevent excess spending during off peak hours. The cloud billing service has two important building blocks: cloud billing accounts and Google Payments profiles. A cloud billing account on the Google Cloud is a cloud level resource managed through the Google Cloud Console, and it's linked to a payments profile. The billing account tracks all costs, including charges and usage credits, for all projects associated with that account. This results in a single invoice and operates in a single currency. The billing account also defines who pays for the resources and includes billing specific roles and permissions. It's managed through IAM roles and can be used to control access to billing related functions. A cloud billing account is linked to a Google Payments profile. This is a Google level resource, not a cloud level resource, and that means that a payments profile can be used to connect and pay for all Google services such as Google Ads, Cloud, etc. It stores essential information such as name, address, and tax ID of the responsible party, as well as details of payment instruments such as credit cards and bank accounts. The payments profile functions as a document center for viewing invoices and payment history and includes user specific permissions to control access to payment related functions. Here is a schematic block diagram of how a cloud billing account and a Google Payments profile are linked. Notice over at the extreme right that we have a payments profile, which is a Google level resource. Then we have the vertical line which separates the Google level resource from the cloud level resources. Everything to the left of that vertical line is in Google Cloud. There we have at the top level an organization node. That organization node has within it a billing account. That's why we say that the billing account is a cloud level resource. It exists within the scope of an organization. The billing account is then linked to multiple projects. Specifically, the relationship between the billing account and the projects is that the billing account is used to pay for the projects and all of the resources within them. The organization owns all of the projects. And finally, the billing account is linked to the payments profile. As this relationship makes clear, projects that are not linked to an active and valid cloud billing account will not be able to use any products or services. This is true even if your project only uses free Google Cloud services. This is an important caveat. Here, we should differentiate between two types of cloud billing accounts. There are self server online accounts and invoiced or offline accounts. A self serve account uses a credit card, debit card, or an ACH direct debit as the payment instrument. Costs are automatically charged to the connected payment method, and you can sign up for a self serve or online account online. That's where the name comes from. Documents such as statements, payment receipts, and tax invoices are generated and accessible in the Cloud Console. In contrast, an invoice or offline account uses payment instruments such as checks or wire transfers. Invoices are sent by email or electronically and can also be accessed in the Google Cloud Console along with payment receipts. Not everyone is eligible for invoiced or offline accounts. Specific eligibility criteria need to be met. There also happen to be two different types of Google Payments profiles: an individual account and a business account. An individual account is used for personal payments, So only the account owner can manage the profile. It's not possible to add or remove users or change permissions. So just one person has sole control over the account. A business account, on the other hand, is for payments made on behalf of a business, an organization, a partnership, and so on. This type of profile allows multiple users to be added and enables shared access and management of the payment information. All users on a business profile can view payment details associated with the account. Finally, there are also two types of charging cycles: monthly billing and threshold billing. In monthly billing, costs are charged on a regular monthly cycle. However, with threshold billing, costs are charged only when the account has accrued a specific amount. Threshold billing has automatically paid cloud billing accounts with automatically assigned payment thresholds. The threshold is a level of spend that, when met, triggers a charge to the primary payment instrument. For self serve cloud billing accounts, the charging cycle is automatically assigned when you create the account, and you do not get to choose your charging cycle. For invoice cloud billing accounts, you typically receive one invoice per month, and the amount of time that you have to pay your invoice is determined by the agreement that you sign with Google. In controlling cloud budgets, the resource hierarchy within the Google Cloud is an important tool. Let's quickly refresh our knowledge of the Google Cloud resource hierarchy. Cloud resources are organized hierarchically. This hierarchy makes it easier to manage access control and permissions. We can attach logical access management policies at every level of the hierarchy. The effective policy at any given point in the hierarchy will be a combination of the policies applied directly at that level or node, as well as those inherited from the parent nodes. This means that permissions set at higher levels in the hierarchy will automatically apply to lower levels unless these are explicitly overridden. This inheritance ensures consistent and efficient management of access control. At the very top of this hierarchy, even above the organization, lies the domain. The domain is the primary identity of the organization. It establishes a company's presence across different Google services, including Google Cloud. We can choose to administer policies universally at the domain level. These will apply to all users and devices. For instance, we might use domain level policies to enable two-factor authentication and resetting of passwords. The domain is linked to either a Google Workspace or a Cloud Identity account. One level down in the hierarchy is the organization. This is the root node in the Google Cloud resource hierarchy. All Google Cloud resources have to be associated with an organization. This allows for the definition of settings, permissions, and policies. Each organization is linked to a single domain. Remember that the domain could either come from Google Workspace or a Cloud Identity account. The organization is automatically created when we set up our domain on Google Cloud. Within an organization, we can have multiple folders. Folders are a grouping mechanism, so they can be used to hold projects, other folders, or a combination of both. Folders must exist within an organization node. Then come projects. Projects are associated with billing accounts, and each project contains resources that are provisioned within that project. Projects are the essential building block for all service level resources, such as Compute Engine VM instances, pub subtopics, cloud storage buckets, and so on. We can also recognize now the relationships that we've already discussed between projects, billing accounts, and payments profiles. Then within projects, we have billable resources. These are the service level resources that we actually use in order to perform operations on the cloud. These are the lowest level of the hierarchy, and all resources must exist within a project. And as already discussed, a project must be associated with a valid billing account. It's also worth discussing labels. These are a way to categorize resources by attaching key value pairs to each resource. Labels are metadata. They allow us to search and organize our cloud assets. Labels are especially useful for very granular cost tracking. For instance, you might assign labels based on the cost center that resources are associated with. It's also a common practice to assign labels such as environment dev or environment prod or test. The resource hierarchy allows us granular access to resources. We can define roles and permissions at different levels, such as the folder, project, or even at the individual resource. Permissions set at higher levels are automatically inherited by lower level resources, but we can explicitly override those at the level of a lower resource. The resource hierarchy enhances security and compliance by implementing the principle of least privilege. Every resource can be assigned the lowest level of privilege and permissions needed for the task of that particular resource. Finally, the hierarchy and especially the use of labels can be used to drive visibility and strong auditing. Next, let's turn to designing an appropriate resource hierarchy for your organization. Let's begin with some factors to consider. The first is deciding who is responsible for cloud resources in your enterprise. Next, what are your specific compliance needs? Are there any region or industry specific compliance needs that you need to keep in mind? And finally, are there significant upcoming business events or corporate actions, such as mergers, acquisitions, or spin offs? Such events can significantly change the organizational structure and resource ownership. That's why it's worth keeping these in mind early in the planning process. Here is a fairly general resource hierarchy design flowchart. We begin by first listing out whether different subsidiaries, regional groups, or business units have vastly different policy requirements from each other. If yes, then we'll have to design for those regions and subsidiaries separately. Google has a recommended design based on regions and subsidiaries, which we will get to in a minute. If not, then we go to the next decision point. Here, we decide whether to give our workload or product teams strong autonomy over policies. If the answer is yes, then we design based on an accountability framework. If the answer is no, then we design based on an application environment. Let's double click into some of those choices. Here is a hierarchy based on application environments. This is obtained from a URL published as a part of the Google Docs. It's visible at the lower left of the screen. At the top level, we have the domain, which is also the organization node in this example. And then we have different folders corresponding to environments such as dev and QA, testing, prod, bootstrap, and shared infra. Within each of these folders, we have corresponding projects. For instance, the dev and QA environment folder has two projects called developer project and QA project. Each of these contains its own resources. We have a similar structure for all of the other folders. It's also possible for nested folders to exist. Notice over on the left, we have some folders which correspond to resources used in multiple environments. These include Bootstrap and shared infra. This hierarchy based on application environments is suitable if you maintain separate environments with distinct policy and admin requirements. Then you might need centralized audit or security enforcement by a central security team across all production workloads or data, or maybe different IAM roles for the cloud resources in different environments. However, you should avoid this hierarchy if you do not operate multiple application environments or if your app dependencies and business processes do not vary much across environments. You also should not use this pattern if you have strong policy differences across different regions, teams, or applications. For more complex corporate structures, including different subsidiaries, regional groups, or business units, we might want a hierarchy based on regions or subsidiaries. Here is an example. At the top of the hierarchy, we have the example.com domain. Then we have different subsidiaries. These are numbered subsidiary 1, 2, and so on. We also have Bootstrap and holding group folders. Then within each of these folders, we have possibly subfolders. For instance, within the holding group, we might have shared infra and then regional folders for APAC, EMEA, and so on. The shared infra folder serves as a common repository for project resources from across all of the holding group. A third possible approach is based on the accountability framework. This is something that we should use where our workload or product teams have strong autonomy over their own policies. For instance, in this case, we will not have a central security team to determine policies for all other teams. Here, we have folders corresponding to functional units such as e-commerce modules or logistics and warehousing modules. There is also reconciliation and billing. These are horizontal services which will be accessed or required by all of the other teams. The Bootstrap folder, which holds all of the common resources needed to deploy Google Cloud Infra, lies directly under the organization node. This type of hierarchy is suitable if your organization has clear ownership and accountability for each product. If the workloads are independent and do not share common policies, or if your processes and external developer platforms are offered as distinct services. In all of these use cases, a hierarchy based on accountability frameworks might work for you. Next, we are going to discuss managing and controlling cloud consumption. Now, enterprises need no urging to control cloud spend, but even so, it's a good idea to define our objectives. Of course, we would like cost savings, but we would also like increased visibility as well as improved compliance, possibly into region specific or industry specific regulations. Enhanced security is, of course, an important end goal, as is better resource management in general. The good news is that the Google Cloud offers a range of services and tools that we can use in order to meet these objectives. These include Google Cloud budgets and alerts, cost management tools to analyze and visualize our cost data, intelligent recommendations. These are actionable and identify idle resources, recommend switching to committed use contracts or right sizing VM instances. And finally, we also have resource quotas. These are a great tool to limit resource consumption for resources like API requests, compute instances, and so on. Let's talk about each of these in turn, beginning with budgets and alerts. This is a feature of cloud billing. Cloud billing budgets help you avoid surprises on your bills. They enable you to track your actual cloud costs and compare them to your planned costs. You can set a budget amount as well as an alert threshold and rules to trigger email notifications. Budgets can go beyond just reporting, however, they can also take actions such as pausing services when spending limits have been reached. Budgets have a number of features that are worth discussing, beginning with flexible time period configuration. So you can specify time periods for your budget that might be monthly, quarterly, annual, or based on custom time ranges. Secondly, they allow customizable scope. For instance, you might define a budget at the level of an entire cloud billing account or for specific organizations, folders, or projects. You can also apply budgets to specific services such as Compute Engine or BigQuery, or even to resources with specific labels. Variable budget amounts are supported as well. For instance, you might have a total amount, or you might base the budget on the previous calendar period spent. There are also threshold based alerts, which, as we discussed, could trigger email notifications when costs exceed a certain percentage of your budget. There are a couple of different ways of specifying alerts. One is using emails, for instance, sending email alerts to billing admins and users, or to project owners, or using cloud monitoring. Alternatively, we might set up PubSub for programmatic notifications. So budget alerts would get sent to an app, and that app could then go ahead and take actions or automate cost management tasks. Google has some great architectural diagrams to highlight how this would work. Budget alerts might trigger emails. There are some rules for who receives these emails. The default behavior is to send the email alerts to billing admins and to users on the budget's cloud billing account, or to project owners on the budget. However, as we can see here, it's also possible to use cloud monitoring to email other people in the organization, such as project managers. In addition to email alerts, we could also have PubSub notifications. Then we could feed these alerts into cloud functions or other sources of compute and use those in order to take concrete action. Here, the cloud function might invoke the billing API in order to explicitly cap spending on the project. Let's move on and talk about the cost management tools which are provided on the Google Cloud. We can access these largely via the console and use these to answer key questions like, how is my current funds spent trending? How do my daily costs compare with those I've incurred in the past or over time? What are my forecast costs based on historical trends? How much am I spending by region? What are the cost of resources with a specific label, such as dev, test, or prod environment resources? Next, let's talk about the intelligent recommendations provided by the Google Cloud using a feature known as Active Assist. This gives automated recommendations and insights on how to optimize cloud resource usage and performance. Active Assist has comprehensive coverage of various Google services, including VMs, databases, storage, and networks. Active Assist is also a proactive tool because it continuously monitors cloud usage and configurations and uses various automated recommendations based on AI and ML in order to proactively identify potential issues before they become too serious. Let's cycle through some of the types of cost recommendations that Active Assist might come up with. These might be about optimizing resource usage. For instance, the Cloud SQL idle instance recommender will identify and suggest removing unused SQL instances. There is also a similar idle VM recommender. The recommendations might enhance performance and efficiency. For instance, there is a BigQuery partitioning and clustering recommender, which guides users on how to partition or cluster tables. It also has a Cloud Run CPU allocation recommender, which suggests switching to always allocated CPU in order to optimize performance. Active Assist is always looking out for cost reductions through commitments. For instance, there's a discount recommender and a spend based commitment recommender, which suggests resource based and spend based commitments. Active Assist also helps with managing and cleaning up idle resources. It has, for instance, an idle custom image recommender, an idle GKE cluster recommender, and an idle persistent disk recommender. Next, let's move on and talk about resource quotas on the Google Cloud. Quotas are used to restrict how much of a particular shared Google Cloud resource you can use. Each quota represents a specific countable resource, such as API calls to a particular service, the number of load balancers used concurrently, or the number of projects that you can create. There are different types of quotas. For instance, concurrent quotas can be used to restrict the total number of concurrent operations in flight at any point in time, usually for long running operations. Allocation quotas are used to restrict the quantity of resources and don't have a rate of usage. For instance, the number of VM instances used by your project at a given time. Allocation quotas don't reset over time. They must be explicitly released when you no longer want them, for example, by deleting a GKE cluster. Rate quotas are typically used to limit the number of requests that you can make to an API or service, and these do reset after a time interval that is specific to the service. We've now discussed multiple proactive budget management tools. Next, let's talk about billing reports, which are a reactive method to control cloud consumption. Billing reports on the Google Cloud provide a comprehensive overview of your expenditures, breaking down costs by projects, services, and resources to help identify significant cost drivers. These are complemented by various other spend related reports, such as the cost table report, which has a comprehensive view of invoice details, including project level costs and taxes, a cost breakdown report, which gives an at a glance waterfall view of your monthly cloud costs and savings, a pricing report, which provides access to Google's cloud service prices. These include list prices, contract prices, and effective discounts. Committed use discount analysis. This is an important discount for many users, and this report helps you to visualize and understand the financial impact of the committed use discounts that you have purchased. Finally, it's also possible to export billing data from Cloud Billing to BigQuery and then create custom billing reports using tools of your choice. You might want to use Looker Studio for building dashboards, for instance. Next, let's talk about some best practices to manage costs. These are more from the organizational perspective. In the context of cost management, Google defines three focus areas: cost visibility, resource optimization, and rate optimization. Cost visibility is about understanding and tracking spend in detail. This would make use of Google Cloud tools such as billing reports. Resource optimization ensures that you use your resources efficiently, prevent wastage and over-provisioning. Examples of this would be right-sizing your VM instances and other resource-specific actions. Rate optimization focuses on reducing the rates at which you are billed for resources. This might use committed use contracts, sustained use discounts, the use of preemptible VMs or spot instances. In order to ensure that all of these are leveraged, Google suggests something known as the Cloud FinOps operating model. This is an operational framework as well as a cultural shift, which is intended to bring together technology, finance, and business in order to drive financial accountability and maximize the value realized from your cloud investments. The Google Docs pose some interesting questions and then set out to answer them. Why does FinOps matter? Well, because it allows enterprises to achieve the full benefits of the cloud. When should FinOps be implemented? According to Google, whatever stage of the cloud journey you are at, FinOps is appropriate for you. Who is responsible for FinOps? Google posits the creation of a centralized FinOps team, which is accountable for implementing and embedding FinOps practices and behaviors. How should FinOps be implemented? Google believes that this framework implements the people, process, and technology focus areas that we've already discussed. So, all of the techniques that we've been discussing so far will all be under the ambit of FinOps. FinOps is based on certain cultural principles which include collaboration, openness, and blamelessness. Accountability for costs should not devolve to finger pointing. That's what this is trying to get across. The FinOps team is responsible for implementing and embedding FinOps practices and behaviors. This does not mean that this central team is meant to take full responsibility for all cost optimizations. Ultimately, empowered workload owners will have to take ownership of their own cloud costs, but the FinOps team can be their thought partners in this. As Google envisions it, the FinOps lifecycle has three phases. The first is called Inform, and this is based on something known as the EPIC framework. Here, 100% of costs must have owners. This is known as Allocate. Report, which means that all cost data should be available and actionable, and Forecast, which means that future spends should be projected and tracked. The next phase is called Optimize. This is where broad methods of making workloads on the GCP more efficient are adopted. This might include product efficiency, that's optimizing resource usage, pricing efficiency, that is reducing the rate paid for resources, and guardrails, that is controlling or actively limiting spend. The third phase is called Operate, and this is where FinOps practices are embedded so that they become business as usual. This includes 5 epics, as Google refers to them: onboard workloads, educate and enable, incentivize, measure value, and fund. The goal is to ensure that FinOps becomes the new normal rather than one-off optimization exercises. The organization has now gone to continuous embedded practices across the entire enterprise. In this context, Google also has some very useful design recommendations for managing costs. The first of these is to consolidate billing and resource management, often by having a single billing account for the organization and by employing internal chargeback mechanisms to allocate costs. If your enterprise has loosely structured conglomerates or resellers, then separate billing accounts might be necessary to meet country-specific tax regulations or individual customer needs. But ideally, stick to one single billing account per organization. Secondly, track and allocate costs using tags and labels. These are essential tools for annotating Google Cloud resources. Tags offer more capabilities such as conditional IAM policies and can be inherited by child resources. So tags are suitable for cost allocation. Labels are fine as well. You can use these to track resource usage across cost centers or other functional groupings. Make sure that you properly configure billing access control. Assign roles such as billing account admin to finance and operations staff. Avoid a single point of failure and use specific roles like billing account user and project billing manager when appropriate. Configure your billing reports to be as usable as possible. Track key metrics such as cost trends, largest spenders, and areas of irregular spending. These reports will provide insights into anomaly detection, trends over time, cost comparison, and validation of billing accuracy. Export this data into BigQuery and then use BigQuery Billing Export and Looker Studio to analyze trends and forecast costs. And finally, optimize resource usage and costs using techniques such as the recommendation hub, purchasing committed use discounts, and other techniques that we've discussed in depth so far. We will now see how the Google Cloud Pricing Calculator can be used in order to estimate cloud costs. So we switch over to a browser window and we hit the URL https cloud.google.com/products/calculator. In the URL that opens up, we start by choosing our base currency over on the top right. Here we see in the dropdown that there is a long list of possible currency choices. For now, USD is what we will go with. Then we click on the big blue Add to Estimate button towards the center left. This opens up a dialog where we can choose by product name. Here you see we have products like Compute Engine, Cloud Storage, Cloud SQL, BigQuery, and scrolling further down, a comprehensive list. Now let's scroll back to the top and choose Compute Engine. We are then taken into a dialog where we can specify various types. The service type right up front, for instance. Here we've chosen instances, but there are also sole tenant nodes and machine images. Then we can configure the number of instances. Let's change this from 1 and make it 5. You can see up top that the estimated cost is now $696.3 per month. Now we can scroll through and keep changing the possible settings and see how the cost changes. Let's change the OS to be paid, that's Ubuntu Pro. The cost goes up to 717.93. In similar fashion, we can then keep scrolling through and experimenting with different setting types. For instance, we can change the machine type, the series, that's N1, N2, and so on, and then also the number of vCPUs. With every change that we make, we can see that the price up top changes as well. Here, for instance, we've used the slider to increase the number of vCPUs. That's now 8, and the price up top has risen to $1252.24 per month. Remember that these are estimated prices. Let's keep going through all of the possible configuration choices. Here we go with SSD persistent disk, set the boot size, add sustained use discounts, and then also change the region. And by the end of this process, the up top estimated price has updated to 1456.94. Now at the very bottom, we see that there are committed use discount options. We haven't selected anything just yet. Let's go ahead and make a 1-year commitment. So we click on that button in the middle and we see that the price drops very sharply to just $951.87. Now remember that all of this so far is only for Compute Engine, and we can see over on the bottom right a total estimated cost across all services, which is shareable. Right now, this only has the Compute Engine costs in there. We'll get to that, but first let's scroll up and add some other products. So we click on the plus add to estimate button on the top right. This takes us back to the list where we can choose different products. So we now add cloud storage here. We then go through a similar process where we estimate our cloud usage. So here we choose a multi-region bucket. We specify the total amount of storage. Again, these are all estimates. And then we also have estimates for our data transfer. Our total estimated cost is now $1,411.87 per month. We see that over on the bottom right. Of that, the cloud storage costs are just $460 per month. We see that towards the top of our screen. Let's keep going and try to simulate a more realistic and full cloud usage scenario. We scroll back up to the top, click on the plus add to estimate button, and this time we choose BigQuery. Then we go through a similar process of estimating our exact usage. So we pick the on-demand edition, location type is set to multi-region, and we also need to estimate the amount of data queried and the active logical storage. By the end of this process, our total estimated cost is now $2343.17 per month, out of which the BigQuery costs are $931.3 per month. Again, please remember, these are all cost estimates. We can now keep adding as many services as we need. So for instance, we might decide to add Cloud Functions or Kubernetes. Here we've added some cloud functions. We spent some time configuring these. And once again, by the end of this process, we have itemized breakdowns. So we have the total cost over on the right and the cloud functions cost visible at the top. The estimated cloud functions cost is $31.93 a month, and the estimated total cost is $2375.1 per month. We quickly hover over the three buttons. The first one has a tooltip Open Detailed View. The second has a tooltip Download.csv. And the third one says New from Duplicate. Let's go ahead and click on the Open Detailed View option. This in turn opens up a new tab where we have the total estimated cost displayed prominently on the top left. And then on the right, we have the breakdown by each of the services. What's great about this view is that we can clearly see how much different options have cost us. For instance, the total estimated cost of our compute engine is 951.87, and we can see that out of that, a solid $829.8 come from the machine type. So that gives us information about where we can tweak our settings in order to potentially reduce our cloud bills. In similar fashion, we can scroll down and view how much our costs come to for each of the other services. Let's return to the main pricing calculator tab and click on the share button over on the bottom right. A new dialog opens up and we can then either download in CSV format or copy the link and share this particular estimate with others. And that gets us to the end of our quick exploration of Google's cloud pricing calculator, which is a very handy tool for estimating your cloud costs. From FinOps to DevOps, I want to talk about cloud reliability with DevOps. And at this point, we will draw a distinction between operational excellence and reliability. Operational excellence in cloud computing focuses on designing and maintaining a robust infra, establishing resilient processes, and utilizing proactive monitoring and response mechanisms. So this is about how the cloud ops are actually run. Reliability, on the other hand, is centered on minimizing downtime, implementing fault-tolerant systems, and employing effective disaster recovery strategies. So as its name would suggest, reliability is all about ensuring uptime and availability. Now, these two terms might seem academic, the difference between them might seem academic, but this distinction had a very real impact because these terms fed into the objectives of two very different types of teams. There were developers who were primarily responsible for writing and deploying code for systems and apps, and then there were operators, ops teams tasked with ensuring the reliable and consistent operation of those systems and apps. This particular organizational pattern had many problems. For instance, it was hard to identify and solve problems because it wasn't clear where the responsibility lay. That in turn came down to the lack of clear accountability for tasks between traditional dev and ops teams. The different reporting lines of these teams also led to communication barriers and silos, and that in turn filtered into inconsistent deployment and environment issues. Now, of course, we all know where this is headed. These problems were resolved by the introduction of DevOps teams. That idea came by blending two different approaches to software development. Traditional software development, which had long phases for plan, design, build, release, and so on, where the cycles could take months or even years, and then agile development methodology, which emphasizes flexibility, collaboration, and iteration. The phases here are build, ship, release, monitor, and improve. And the ideas and philosophy of agile development led to DevOps, which is effectively a merged version of development and operations. And that in turn led to CI/CD, which has to do with continuous integration and continuous delivery or deployment. Here is a schematic block diagram of how the CI/CD process works. There is the application code. It gets committed to a repository such as GitHub. Then it gets built in automated fashion. Immediately after that, tests kick in. These range from unit tests and integration tests and everything in between. This pipeline so far refers to continuous integration. This is a development practice where developers frequently merge their code changes into that central repo. Each integration is automatically built and tested to detect integration issues early, and this then feeds into the next step, which involves pushing to staging and production. This is called continuous delivery, and here the code changes are automatically prepared for a release to production. Once the code passes all automated tests, it's deployed to a staging environment. From that staging environment, it may be pushed either manually or automatically to production. If that push from staging to production is manual, then this pipeline is said to be a continuous delivery pipeline. On the other hand, if that last step is automated, then it's called a continuous deployment pipeline. To summarize some of the key points of the DevOps principle, it stems from the agile methodology because it has teams working together across the entire product lifecycle. Developers, testers, release engineers, IT ops all work together collaboratively and, very importantly, iteratively. The iterative nature of the Agile platform informs the CI/CD pipeline. The DevOps approach relies heavily on automated tools because it needs a feedback loop where software improvements are incorporated and released faster and faster. Key principles of DevOps start with collaboration, visibility, and alignment. The collaboration exists among cross-functional teams, including developers, operations, and QA. DevOps emphasizes ownership and accountability. Teams are responsible for the entire life cycle of the application from development right to deployment and beyond. Shorter release cycles and iterative development are very important in the DevOps world. This approach helps in quickly addressing user feedback, reducing time to market, and minimizing the risk of large, infrequent Big Bang releases. A key tenet of DevOps is a commitment to continuous learning and improvement. Teams regularly meet to reflect on their processes and learn from success and failure, and thereby make iterative improvements. The DevOps approach heavily informs cloud architectures because DevOps practices have informed cloud services. Continuous integration, which involves the frequent merging of code changes into a central repo, followed by automated builds and tests. Continuous delivery, which extends continuous integration by automatically deploying code changes to a staging or production environment after the tests pass. Automation, using tools and scripts to automate repetitive and error-prone tasks. That automation extends beyond code to even infrastructure, and that leads to infra as code. This is the practice of managing or provisioning compute using machine-readable scripts. For instance, the Google Cloud Deployment Manager or Terraform. The microservices architecture, which involves breaking down applications into small independent services that can then be developed, deployed, and scaled individually. And finally, monitoring. This involves continuously observing patterns, apps, and infra to ensure that they are running optimally, spot anomalies, and detect issues before they actually impact users. Tying together all of these best practices gave rise to a new discipline, SRE or Site Reliability Engineering. This combines software engineering and IT operations to create scalable and highly reliable software systems. SREs are an integral part of the DevOps paradigm. Within the DevOps paradigm, SREs, that is, Site Reliability Engineers, focus on automating routine operations tasks such as deployment, monitoring, and incident response. They help with a unified approach to building, deploying, and maintaining software, and ultimately help to implement CI/CD and drive the success of DevOps initiatives. The entire discipline of site reliability engineering is based on some important concepts of reliability. Google refers to these as the four golden signals of reliability. These are latency, traffic, saturation, and errors. Let's talk about these in turn, starting with latency. Latency refers to the time that it takes to service a request. This includes both successful and unsuccessful requests, so failed requests will contribute disproportionately to latency. Monitoring latency helps to understand the responsiveness of a system and helps in identifying performance bottlenecks. Latency is important in two different ways. For one, it's a direct driver of user experience, and secondly, an increase in latency indicates that a system might be under stress or near its capacity limits. An overloaded system will witness an increase in latency, and that's driven by an increased traffic. Traffic is the second of our golden signals. It measures the demand on a system. It's typically quantified in terms of the number of requests per second. Monitoring traffic helps in assessing load on the system as well as for planning capacity. Where latency is, in a sense, an outcome of our system, traffic is a predictor or an input metric. It's a crucial indicator of current system demand, and it can be used to predict changes in latency down the road. Because traffic is a forward looking metric, monitoring traffic helps organizations make decisions about scaling resources and managing infra costs. Understanding traffic patterns also helps in identifying unusual spikes, which might be indicative of security issues or bugs. A third signal worth tracking is saturation. This indicates how heavily utilized system resources are. This might be CPU usage, memory or disk I/O usage, or indeed any measure of the capacity of a system. A measure of saturation tells us how full the service is and how close it is to the limits of its capacity. It's important to constantly monitor saturation because this helps to prevent overloads. When a system approaches saturation, the performance will typically degrade, possibly resulting in errors. These are the fourth golden signal. Errors represent the rate of failed requests or operations. The error rate highlights issues that prevent the system from functioning correctly. Errors are in effect feedback from the environment. These are vital indicators telling us that something is failing in the system. This might be due to misconfiguration problems, capacity issues, or software bugs. High error rates might also lead to violations of service level objectives, and these in particular will warrant immediate attention. As with all of these metrics, monitoring errors is important. It enables a rapid detection and the diagnosis of problems before they become catastrophic. Let's switch now to three other foundational concepts in site reliability engineering: service level indicators, service level objectives, and service level agreements. These are also worth understanding in detail, so let's talk about each, starting with the SLIs. Service level indicators are specific metrics used to measure the performance and reliability of a service. They provide quantitative data on various aspects of the service, such as the golden signals, latency, error rates, and so on. They might also measure throughput. These help to assess whether the service is meeting its desired performance criteria or not. Let's take a concrete example. For a service like Google Cloud Compute Engine, an SLI might be the uptime of VMs. Measuring this uptime is essential to understand how well the VM service, that's GCE, is meeting its intended operational goals. Different services have different service level indicators. So while uptime might be a suitable SLI for GCE VMs, for an API server, we need something different, maybe an error rate. But SLIs are crucial because they help to determine whether the service is meeting its service level objectives or SLOs. Service level objectives are explicit targets for each of the SLIs. SLOs define the desired level of service performance. These are clear and measurable goals for metrics like uptime or response time, and these serve to guide engineering efforts as well as operational decisions. SLOs set the standards for acceptable performance. For instance, in a cloud-based VM service, an SLO might specify that 99.9% of VM instances must have an uptime of 99.99% over a rolling 30-day period. They help to define the desired level of service performance. In a way, they function as targets. The SLI must be related to the SLO. So if a particular service has an SLI of error rate percentage or uptime percentage, then the SLO will be a target for these metrics. SLOs are still internal targets, but at some point, These get translated into SLAs or service level agreements, which are in effect binding commitments, formal contracts between the service provider and its customers. SLAs or service level agreements specify the expected level of service performance as well as the consequences of failing to meet these expectations. SLAs, that is service level agreements, will typically include specific SLOs, that is service level objectives, and also outline remedies such as service credits if the service does not live up to its commitments. It's important to remember that SLAs are formal contracts between the service provider and the customer. The SLA will be defined in terms of the same metric as the SLI. For instance, the percentage of successful API calls or the percent of time that VM instances are up. In this regard, they are similar to SLOs, but unlike SLOs, they define the terms of a business relationship. So, to this extent, they are external and there are penalties for non compliance. All cloud providers have SLAs on their products. Here is an example of Cloud SQL's SLA. We can see here, for instance, that Cloud SQL Enterprise Plus with high availability offers greater than or equal to 99.99% uptime. On the other hand, the Cloud SQL Enterprise Edition with high availability but with the plus missing only offers 99.95% as the SLA. Here, the SLI is the monthly uptime percentage. But wait, this SLA is not complete. We also need to specify the penalties for non-compliance. Here we can see what Google promises to customers who do not experience the required level of service. For Cloud SQL Enterprise Plus with high availability, this is a table where, based on the monthly uptime percentage, we get back a percentage of our monthly bill on this particular service. For instance, Google is telling us that if we experience uptime of less than 95%, they will repay 100% of our monthly bill on this particular service. So the penalties to Google in case of not delivering are very real. Let's compare this SLA to that for Cloud SQL Enterprise, not Enterprise Plus. Here we can see that if we experience uptime of less than 95%, Google only promises to refund 50% of our cloud bill. This is an excellent example of how all of the hyperscalers adhere to SLAs on all of their services. The Google Cloud Digital Leader curriculum includes topics related to resilient infrastructure and processes. Let's define this term and make sure that we've covered all of our bases here. Resilient infra and processes refer to the design and implementation of systems and procedures that can withstand and quickly recover from disruptions, failures, or unexpected events. The term resilience in general measures the ability of a system to bounce back after a problem. Cloud-based architectures have 5 specific patterns that are used in designing resilient infra and processes: redundancy, replication, scalability, backups, and automation. Let's understand each one in turn, beginning as usual with the first, that's redundancy. Redundancy involves creating multiple instances of critical system components in order to ensure continuous operation in case of failure. Redundancy can be achieved by duplicating hardware, software, and network resources and having systems to automatically switch to these backup components when the primaries fail. Key aspects of redundancy to keep in mind are that it mitigates a single point of failure by having redundancy. This may be implemented at the hardware, network, or application layer, and it all comes down to duplication of critical components or resources to increase availability. Next, let's talk about replication. This is especially common in the cloud because data tends to be replicated across regions. Replication usually involves copying data and services across multiple geographic regions in order to ensure availability and resilience against regional failures. So, as the term replication suggests, this involves creating multiple copies of data or services and distributing them. This is specifically often done to minimize the impact of hardware failures and outages. And on the cloud, the most common form of replication is of data that is replicated across zones or data centers in different regions. The next pattern for designing resilient infra and processes is scalability. This refers to dynamic provisioning and elasticity. Scalability refers to the ability of a system to adjust resources dynamically in response to changing demand. A subtle difference between elasticity and scalability is that elasticity implies scaling both up and down, and usually this scaling is automatic. The fourth technique to achieve resilience is taking a lot of backups. This might seem very simple, but it's done very systematically, which means that they are automated and stored in secure storage. Also, ideally, the backups should be stored in geographically separate locations. The final concept here is automation. Automation adds to resilience because it reduces the chances of manual error. Automation can come in the form of scripts and automation tools to handle repetitive and complex tasks, and it helps systems to quickly respond to failures or to performance issues without the need for manual intervention. We will now talk about observability tools on the Google Cloud. This refers to tools for the analysis of metrics, logs, and traces. These used to be known as the Stackdriver suite many years ago. Observability on the cloud refers to the ability to monitor, measure, and understand the internal states of cloud based systems through the collection and analysis of metrics, logs, and traces. Observability is a crucial part of ensuring site reliability. Observability has several different dimensions. Let's talk about some of these. Metrics. These are numeric data points that track the health and performance of systems over time. Examples could include CPU usage or request latency. Sudden changes in metrics probably signal potential issues that need investigation. Logs are records of system or app activity, time-stamped in order to provide a chronological sequence of events. They provide detailed information about specific actions and help also with auditability and traceability. That brings us to traces. These differ from logs in that traces map the journey of a request through various parts of a distributed application. Logs, on the other hand, only show all of the actions within the context of one part or one service. In addition to metrics, logs, and traces, it usually also helps to have additional context, such as, for instance, user information, which we monitor while analyzing metrics, logs, and traces. This gives us a holistic view of the user or the system application. Observability tools bring with them a number of benefits. They help to deal with the complexity of cloud systems. They help to collect and analyze meaningful data from across an entire ecosystem. And perhaps most importantly, they give a comprehensive and holistic view of the environment. Google Cloud has a number of observability tools. These are named Cloud Monitoring, Cloud Logging, Cloud Trace, Cloud Profiler, and Error Reporting. Let's talk about these in turn, starting with Cloud Monitoring. Cloud monitoring itself provides different services that can be used to understand the health and performance of apps as well as of Google Cloud services. These include alerts and notifications, proactive monitoring and validation. These might take the form of uptime checks for endpoint responsiveness or broken link checkers for web pages. Data visualization capabilities include dashboards and charting. Dashboards could be either auto-generated or customizable, and the Metrics Explorer is used for quick visualization of time series data. Data collection and storage via cloud monitoring can be used for system metrics across Google Cloud services. There is a wide range of metrics that are collected through the service. These include metrics collected by an ops agent, user-defined metrics, external metrics, Prometheus metrics, and log-based metrics. That leads nicely into our next service, which is cloud logging. This is a real-time log management system with storage, search, analysis, and monitoring support. Cloud logging collects logs from a variety of sources. We can instrument our apps using client libraries, use the ops agent to collect logs from std out or standard error, configure the ops agent to collect logs from third party applications, and then once we've collected all that data, use it to troubleshoot logs. Cloud logging has two main interfaces for log analysis: the Logs Explorer and Log Analytics. Logs Explorer is better for viewing individual log entries, but Log Analytics lets you run SQL queries for aggregate operations. Both of these are accessible through the Cloud Console. You can also use them programmatically through the Cloud Logging API or the Google Cloud CLI. Cloud logging also has support for monitoring logs. We can create log-based alerting policies for important but rare events, or log-based metrics to monitor trends over time. The next offering from Google Cloud's observability tools is CloudTrace. This is a distributed tracing system which helps in analyzing the latency of applications. It collects latency data from various Google Cloud services as well as from apps using the CloudTrace API. This can then be used to gain insights into application latency, including the ability to analyze how request processing times changed over time. You can also use it to compare latency between different requests and to identify dependencies within an application. CloudTrace has two main features: Trace Explorer and Analysis Reports. The Trace Explorer is useful for examining individual traces in detail. The analysis reports are better for creating custom reports to compare different sets of latency data and apply filters for specific trace subsets. Cloud Profiler is a service that continuously gathers and analyzes performance data from production applications. It is a low overhead profiling tool which makes it fine even for continuous monitoring of production systems. It will not interfere with a production system or hurt its performance. The profiler supports different types of profiling across different programming languages, including Go, Java, Node.js, and Python. It collects metrics such as CPU time, heap usage, allocated heap usage, contention, threads, and wall time. And the last service in this suite is error reporting. This is a service that aggregates and displays errors from running cloud services and provides a centralized error management interface. The error reporting service collects errors in two primary ways: either from cloud logging, that is, by detecting properly formatted error log entries, or by receiving errors that were passed in directly through the error reporting API. We will now run through some topics that are a part of the Google Cloud Digital Leader curriculum. These include Google Cloud's customer care. There are multiple different customer support options on the Google Cloud, and we will quickly examine each one of these in turn. These are named quite self-descriptively: basic support, standard support, enhanced support, and premium support. Let's start with basic support, which, as its name would suggest, is effectively the starter option. Basic support is free and included for all Google Cloud customers. It provides, of course, access to documentation, but also community support, cloud billing support, and Active Assist recommendations. Remember that Active Assist is a suite of tools that generate insights and recommendations to help you optimize your cloud projects. Next, we have standard support. This option is suitable for development or test environments, that is, when your app is being constructed. It comes with expert assistance that can help you get up and running with the cloud. It includes unlimited English speaking support representative access, that is, during working hours 5 days a week. And lastly, it includes access to the Cloud Support API. Then we get to enhanced support. This is a higher tier, of course. It's aimed at production workloads. It has comprehensive support features like technical support escalations and third-party tech support. They help you resolve multi-vendor issues as well as case escalation. It also offers API integration with the Cloud Support API and the Active Assist Recommender API. You can avail of multilingual support in Japanese, Mandarin, Korean, and French. So this is suitable for global organizations, and it has some additional value-added services such as a technical account advisor service and a planned event support service for managing peak events. That brings us to the highest tier of customer support, that's premium support. This tier is designed for critical workloads and comes with a dedicated technical account manager as well as customer aware support, where the customer care team maintains detailed information about your architecture, partners, and projects. It has comprehensive other services such as Google Cloud Skills Boost training platform credits, as well as operational health reviews so that you can carry out proactive optimization. Next, let's talk about the life cycle of a support case. This is what happens when you contact Google customer support. There is a large number of possible interactions between you and the support team. Let's go ahead and try and make sense of these. To begin with, the customer initiates a support request and provides the relevant details. These include error messages, logs, and steps needed to reproduce the problem. A key part of this process is that the user selects a priority level from P4, that's low impact, to P1, that's critical impact. Based on this information, a triage process is undertaken. The support team examines that information to determine the severity, and they might ask for more details or clarifications. If it's a simpler query, the customer care representative might be able to resolve the issue right away. For simple cases, it ends right here. The support engineer solves the case and the customer validates the solution. For more complex cases, the case gets assigned to a support engineer. The next step then is troubleshooting and investigation, where the team digs into the information that's been provided. During this troubleshooting and investigation, the customer care team keeps in regular touch with the customer. At this point, this might also require collaboration with other internal teams. Once the root cause is identified, there are different ways in which the issue might be handled. Ideally, the issue can be resolved right here, or a mitigation plan can be provided. Or else, this might require consultation with higher level support or engineering teams. In some cases, this might even lead to the creation of a feature request that's sent to the engineering team. After implementing the resolution or the mitigation plan, the customer care team will work with the customer to ensure that the solution is effective. They might ask the customer to run certain tests or provide feedback on how things are working. And then once the customer validates the mitigation, the support case is closed. The team will then prepare a summary of the resolution, document the steps taken, and ensure customer satisfaction. They may also offer recommendations for preventive measures for the future. The customer receives a feedback survey, allowing the support team to learn from their experience and improve their services. If the support case gets stuck, you could choose to escalate it by moving forward. Escalation is meant to flag process breaks or for the times where a case is stuck because of a breakdown in communication between the customer care representative and the customer. There are some potential downsides with escalation, notably that it disrupts the workflow of the customer care team and can potentially lead to delays in other cases. So, escalation may not lead to a faster resolution, it might even slow things down. Finally, for high impact cases, the most effective approach is to ensure that the case is set to the appropriate priority level. This will ensure that the case is assigned to the right resources quickly without the need for unnecessary escalation. Google takes sustainability very seriously, and that's why there is a learning objective related to sustainability on the Google Cloud. Google is rightly proud that its data centers were the first to achieve ISO 14001 certification. This is an internationally recognized standard for environment management systems. Google's data center in Hamina, Finland is famous for its innovative and sustainable design, located in a former paper mill and uses seawater from the Gulf of Finland for cooling, making it one of the most energy efficient data centers in the world. Here are some key milestones in Google's sustainability journey. In its first decade, it became the first major company to be carbon neutral. Achieving carbon neutrality means that a company offsets its carbon emissions by investing in projects that reduce carbon dioxide and therefore has a net zero carbon footprint. In its second decade, it achieved 100% renewable energy. This term implies that it matches all of its electricity consumption with purchases of renewable energy, such as wind or solar power, on an annual basis. Google also aims to be the first major company to operate completely carbon free by 2030. The term carbon free means that the company's operations produce no carbon emissions at any time, using only energy sources that do not emit carbon dioxide, such as wind, solar, or hydroelectric power. Google Cloud has a service called Google Cloud Carbon Footprint. This is not a traditional service like cloud storage or compute engine. Rather, it has comprehensive emissions reporting so that users can estimate and reduce the carbon footprint that they have from using Google Cloud services. So, this service helps organizations to accurately measure and report their own cloud related carbon emissions in line with the GHG protocol. This service has granular analysis and visualizations, including an in console dashboard for high level overviews of carbon emissions, and it can also export its data to BigQuery. The documentation here is based on a methodology that's been validated by third parties who are experts in sustainability consulting and thereby provides credibility and assurance to enterprises looking to use this service for their own emissions reporting and sustainability initiatives. We started this course off by understanding the Google Trust Principles and data sovereignty considerations. We explored how these principles ensure data security and compliance with international regulations. Additionally, we examined Google Cloud Compliance resources, which provide guidelines and tools to help organizations meet their compliance requirements. Next, we learned about financial governance on the cloud and the best practices for managing cloud finances. We studied Google Cloud resource hierarchies to understand how to organize and manage resources effectively. We also learned how to control cloud consumption and explored various cost management tools on Google Cloud, including the Google Cloud Billing Calculator to monitor and optimize expenses. Finally, we learned about observability tools on Google Cloud that help monitor and maintain system performance, such as logging, monitoring, profiling, tracing, and error reporting. We explored cloud reliability with DevOps and the basic concepts of reliability in cloud environments. Additionally, we examined Google Cloud Customer Care, support services, and the life cycle of a support ticket. In conclusion, we built a strong foundation in data security, financial governance, cloud ops and support, and cloud reliability. That gets us to the end of this learning path on the Google Cloud Digital Leader certification.